Yeah. So good to start. Very good morning to all the participants and all the experts invited for this webinar. I'm Bhaskar Gaikwad, convener of this national webinar on abiotic stress in agriculture, geospatial characterization and management options. I welcome you all. To start with, we have a very learned and accomplished researcher from the area of climate change with us, who has more than 13,000 citations to his publications at his credit, and is also currently the director of National Institute of Abiotic Stress Management, Dr. Himanshu Pathak, sir. Praveen, can you please stop the videos of who? Yeah, please. So we have with us Director of National Institute of Abiotic Stress Management, Dr. Himanshu Pathak, sir. I request Director of ICR NISM, Dr. Himanshu Pathak, sir, to give his introductory remarks and set the stage for the webinar. Sir.
Okay, thank you very much, Dr. Bhaskar. Praveen, can I share my screen? Is it visible? Praveen, I think you have to allow me to share.
Yes, sir. Yes, sir.
Yes, sir.
Is the screen visible?
Now, sir, please share your screen, sir.
Okay. It shows that sharing has been paused. Praveen, can you check whether there is something?
Sir, please make it in presentation mode, sir.
Okay. Is it visible now? Praveen, is it visible? No.
Screen is visible, sir, but all slides, it is not in presentation mode, sir. Now it is visible.
Nice. Okay.
Now it is okay. Now it is okay.
Okay. Very good. Okay, friends, it is indeed a great pleasure for me and all the staff of Miazam Baramati to welcome each and every one of you in our national webinar on abiotic stress in agriculture, particularly geospatial characterization and management options. Friends, I would like to welcome all of you with our institute song.
यहाँ खोज पर तनाव मुक्ति का नारा है, अजय स्ट्रेस प्रबंधन संस्थान हमारा है। यहाँ सोच नई पर ध्यास वही, किसान कल्याण की आस वही, उन्नत खेती की जब प्यास बढ़ी, बुनियाद नियासम की खड़ी, कृषि परिषद का विश्वास है, विज्ञान जगत का कौशल भी अनुसंधानों का रुख बदलाव में सहारा है, बारामती में रुख बदलाव में सहारा है, अजय स्ट्रेस प्रबंधन संस्थान हमारा है। उपज क्रांति के गहरे मिलेंगे।
Friends, am I audible?
Yes, sir.
Okay, so let us start with. As you know that our institute is working on abiotic stress management. So before I request all our speakers to go on with the proceedings, let me very briefly tell you what exactly we are doing and what we are expecting from this particular webinar today. Friends, all of you are very much familiar with stress. But what is this stress actually? It can be defined in many ways. Physically, stress is a force per unit area. Chemically, they define it as a trigger that alters the normal chemical process. Biologically, the stress is a stimulus that affects growth of any organism. And of course, psychologically, all of us know what the stress is, so I shall not mention about that one. The stress could be of two types: abiotic, which is basically physical or could be chemical, and of course, biotic, which is biological. Unfortunately, all kinds of stresses, whether it is biotic or abiotic, that affect agriculture. In abiotic stressors, it could be moisture stress, drought or flood, nutrient stress, high or low, radiation, temperature, pollution, salinity, mechanical, and so on. And wherever there is any stress, the productivity goes down. And unfortunately, again, most often, if not almost always, agriculture is subjected to various kinds of abiotic stresses. Another very important point is all these stresses are actually intensifying. The climate change is aggravating, and if you see recent Umphan and Nisarga, water stress is also increasing, soil quality is declining, environmental pollution, whether it is soil pollution, water pollution, or air pollution, is accelerating. Biotic stresses, even recent locust attack, is also getting more and more intense. And of course, all of us are passing through COVID-19 and national lockdown, and we understand very well. The projection is that all of these stresses, particularly the climatic ones, atmospheric ones, are going to intensify in times to come. Not only their frequency is going to increase, but the intensity is also going to increase. Whether it is cyclone, heavy rain, heat wave, flood, drought, all of these are going to intensify in times to come. But the irony of abiotic stresses, for example, say climate change, is that the poor farmers or any person who is poor, they are going to be affected the most. Though they do not contribute much to the problem. For example, our poor farmers or poor people, they do not contribute much to climate change. They do not emit large amount of greenhouse gases. But whenever the adverse impacts will come, they will be suffering the most because they depend more on stress-sensitive natural resources. Therefore, this is the biggest irony of any of these abiotic stresses. Now the question is how to manage all these stresses, particularly the abiotic stresses. And for that, we propose that there is a model, we can call it as Farm B model. The approaches should be first foresee the stress, which you can call it as forecasting. Then adapt the stress, call it adaptation or adapting with the changes. Respond to the strain, so response measure or responding. Mitigate the stress, reduce the stress if possible, we call it mitigation. And of course, finally, very, very important, build capacity to manage the stress or capacity building. So this can be called as Farm B approach for managing abiotic stresses. But then how to do it? That's probably the bigger question. I can tell you that there are 5 aims which are very, very important, or these are the keys of managing abiotic stresses. These are first, measure the stress. What they say that anything which is measurable is manageable. You cannot manage anything if it cannot be measured. So this is the first and foremost principle of managing anything. First, you have to measure it. Second one is, of course, if you can, you map it. So map the stresses. Then you model it. You link it with several other parameters so that you know the relationship, which factor is going to intensify and how it is going to affect. Then you monitor the stresses. And finally, you will be able to manage the stresses. So these are 5 aims, which are the important keys for managing abiotic stresses. But how to measure, how to map, how to model, how to monitor, and finally, how to manage. Fortunately, there are very good advanced technologies and tools available with us today. We have got high resolution satellite data. We have got drones, GPS, GIS, simulation models, decision support systems, artificial intelligence tools, robotics, and a number of other ICT tools. All of these tools can really help us in measuring, mapping, modeling, monitoring, and finally managing the abiotic stresses. Just with this diagram, you'll be able to understand a little better. What we can do with all these ICT tools is that we can spatially and temporarily measure and map, for example, climatic stresses. Similarly, we can map soil and water processes with spatial as well as temporal distribution. Then we can use some kind of models, maybe crop model, animal model, could be mechanistic model, could be empirical model. And then over and above, we put management options. And once we do that, again, using these particular tools, we will be able to know the spatial as well as temporal distribution of productivity of crops and animals, income, ecosystem services, sustainability, and many other parameters by doing these steps. So if you have to understand and summarize all of these things, friend, over the years, our science has really progressed a lot. Science in the field of plant, animal, environment, and so on. And at the same time, we have also been able to develop technologies, whether it is space technology, information and communication technologies, various technologies in agriculture. So when we combine these technologies and science, we integrate them, which you can call them as knowledge integration, and put them everything into some kind of simulation models. And then over and above, we put the geospatial distribution of soil, weather, water, socio-economic aspects, and also the stakeholders' goals, farmers' goals, for example, what farmers want, what are their priorities, where are the provisions and opportunities for increasing their productivity and income. So when all of these things could be put together in a system basis, then we will be able to come out with several options. We will be able to know the options for development, like what kind of production of what kind of crops or animals can be grown, what kind of production resources will be required in terms of irrigation, fertilizer, machinery, seed, labor, and so on. We can also know what are the socio-economic achievements like income, employment, equity, and of course, what are going to be the environmental and climate impacts, how much amount of greenhouse gas are going to be emitted, how much could be carbon footprints, pollution load, and all of these things we can know by putting everything in this kind of abiotic stress information system, or ASIS, which we call. Friends, you'll be very, very happy to know that our institute, National Institute of Abiotic Stress Management, is working on this particular aspect for it since its inception in 2009. And we work with one mission, and the mission is managing abiotic stresses for sustainable agriculture. We work in 4 schools: School of Atmospheric Stress Management, School of Drought Stress Management, School of Abiotic Stress Management, and School of Policy Support Research. Very recently, we have formulated our new projects. We have got 4 umbrella projects, 4 flagship projects, and few other in-house projects. One of our umbrella projects is on abiotic stress information system. There, we are doing geospatial digital maps of multiple abiotic stresses, management options, and future scenarios. Here, what we want to overlay all this information, which I was just mentioning, and then at the end, we would like to come out with a central repository of primary as well as secondary geospatial temporal data sets for multiple abiotic stresses. We also want to develop repository of geospatial management options. We want to also analyze the future scenarios through vulnerability assessment at district or even other levels, and also develop GIS framework for generating geospatial digital maps based on user different queries. We would like to come out with few products like data sets of weather, drought, flood, cyclone, salinity, aridity, mineral stresses, and so on. We would like to develop multiple abiotic stress maps of vulnerability, management options, future projections for several commodities, including crops, livestock, fisheries, and we'll be using tools like vulnerability assessment, scaling up approach, integration, and so on. Therefore, in this particular national webinar on abiotic stress in agriculture, geospatial characterization and management options, we are really looking forward for your inputs, for your expert opinion and knowledge. And here our specific objectives are to identify the sources of abiotic stresses in agriculture. Secondly, to explore the methodology for their geospatial characterization. Thirdly, to identify the management opportunities for reducing abiotic stress in agriculture. And finally, to build awareness, learn lessons, and impart knowledge on abiotic stress management. Friends, as you all can see, and we'll be listening to all of them, today we have with us very eminent speakers who have got enormous experience on all these fields. We have with us Dr. Giriraj Amarnathji, we have got Dr. Chandrasekhar Biradar, we have got Dr. Paresh Srishan, Dr. Rajiv Srivastavji, Dr. Pradeep Dey, Dr. KP Suresh, and of course all of you. And whenever you find time, we shall request you also to participate in the discussion and give your very valuable suggestions. I also thank the convener and co-conveners, convener Dr. Bhaskar Gaikwad, who has taken very keen interest in developing the whole program and very passionately working on our ASIS project, Abiotic Stress Information System, and also our co-convener, Dr. Sachin Kumar Pawarji. So I thank both of them for taking initiative and organizing this particular national webinar. Along with them, the whole institute, all the staff of Niyazam Baramati have been associated with this particular event. Friends, again, I welcome each and every one of you to our institute, of course, virtually. And we really look forward, not only for today's webinar, but also in times to come to collaborate with all of you, to get your suggestions, to get your feedback, so that we will be able to succeed in our mission of managing abiotic stress for sustainable agriculture. With this, I once again thank each and every one of you, and I request Dr. Bhaskar Gaikwad to please proceed
He will be under
of the national webinar. Dr. Bhaskar, please.
Thank you, sir. Praveen, you can please mute the other disturbances in between. To start with, in fact, we have got Dr. Giriraj Amarnath, sir, who is a research group leader with Water Risk to Development and Resilience at International Water Management Institute, and he's based currently in Colombo and Sri Lanka. To introduce Dr. Giriraj Amarnath, in meantime, sir is sharing the screen. Dr. Amarnath is a remote sensing researcher specialized in application of remote sensing and geographic information systems in the study of risk assessment across a wide range of natural hazards and monitoring land and water resources in Asia and Africa. He has over 13 years experience in research, including 3 years in academics at University of Beirut, Germany. He has expertise in several areas, including monitoring flood and drought, rapid emergency response mapping, remote sensing data and image processing, geographical information systems, satellite-based rainfall estimates, drought forecasting, hydrological modeling, flood forecasting and inundation, a long list. And one more important is the weather index insurance and food security, the climate change and the disaster risk management. He has published several research papers in international journals with high impact factor, and is also recipient of several awards. For Whitley Award from UK Conservation Grant, Young Scientist Award Competitor Award. Then he has also received prestigious grant from American Rhododendron Society for mapping and monitoring the rhododendron distributions in Western Ghats, and many more. With this very brief introduction, I request Dr. Giriraj Amarnath, sir, to please deliver his presentation on the very pertinent topic, understanding climate risk in promoting agricultural risk solutions to geospatial techniques.
Thank
So
you.
I hand over to you. Yeah.
Yeah, thank you, Dr. Bhaskar. I am audible.
Yes, sir. You are very much audible.
Thank you. And it's a great pleasure to be here on this important webinar. And I must also congratulate the director, Dr. Himanshu, for leading this initiative, which is a very at a timely period given the scale of excess moisture happening in large part of the state in India. And it also set a tone of what's the background and objective of this Abiotic program being led by the center itself. And it's also helpful for speaker like me to know really the background of what the abiotic stress is about, because I'm not a clear expert in this field, but we will relate with the resilience measure what we are doing on. So this particular presentation is based on the practical evidences we have been doing and how the geospatial information has been used in a number of CGR projects which we are leading on. With that, I would begin my background of International Water Management Institute. Maybe some of you are not aware of where we are and what we are doing. A quick 3 slides about my institute. So basically, we are one of the members of CJR. CJR stands for Consultative Group of International Agriculture Research. And we recently adopted a new strategy last year, and we are looking for a science for a transformative agenda in the sense it looks at policymakers to private sector to development planners to look at more innovative transformations, how science-based information or the tools, models that can be utilized in the years to come to look at solutions in sustainable development, in look at areas where we can provide much more progressive climate resilience program in the years to come. So we have a strategy for the next 5 years, and some of these work what I will be presenting and the scope of this webinar will briefly address those elements of the topic. So within this water challenges, I think when we are speaking about abiotic stress management, it's not just about physical, chemical, or psychological, but also we look at, yes, these are at a very fine scale we need to look at, but the broad elements what we are looking at is about sustainable food system, understanding the resilience of the climate, like Dr. Himanshu mentioned about understanding the current and future risk. And this is where the Abiotic research program, we are working in the climate program, looking at water-related disasters and how disruptive technologies like geospatial modeling tools, including machine learning algorithms, are being used in our institute to address these solutions, which is very pertinent, not just only in India, but elsewhere as well. And equally, we are looking at growth, because at the end of the day, we can provide all solution, but from the farmer's perspective, it's all about growth. And also at the policymakers or at the government level, we need to have more inclusive program. That's where we focus on. With this, I also want to just say that our presence is not just limited to headquarters in Sri Lanka. We have presence in all these countries. We work and do projects for over 65 countries as of last year. So it's a very renowned and global institute when it comes to water management. With that, I will step into the topic of discussion. I don't want to go more detail on the stress that was already presented by Dr. Himanshu, but basically when you look at the landscape, you will look at multiple stress, whether it's a drought or a flood or a chemical related stress, which is already discussed in the previous speaker. What is important to understand is that how does this climate risk is going to impact both current and future, and how does the response to those biological stress will change in rising temperature to heat waves or whatever the stress that will pertinent or excess the soil moisture, and overall how does it impact the cropping system, and one how that best we could prepare the abiotic stress management given the understanding and characterization of this climatic process. In my presentation, I'm not discussing more on the chemical side or on the psychological aspect, but more on the biophysical aspect of the abiotic stress management. And the other aspect, when I was looking at literature, we talk about technology and management. Even the Center Indian Council of Agriculture Research have developed a series of drought tolerant seed varieties or flood tolerant seed varieties. In this case, the Sorna sub 1, which is now widely being used in large part of the floodplain regions, where there has been a successful evidence of how such agriculture technologies can reduce the stress factors from the climate aspect. Whether it is also, there are like states like Orissa or West Bengal, now they are introducing a lot more salt tolerant. Likewise, other states are introducing heat tolerant. So while technologies are increasingly going on the biotechnological aspect, equally we need to understand the spatial aspect of abiotic constraints that we are experiencing in a large scale. And over years, we worked with the Indian Institute of Water Management. It's another ICR center where we have seen that while we know the flood pattern or the drought happening, we could able to ensure through the advisory, climate advisory information, shifting the sowing dates or shortening the rice variety or any crop system, and also ensuring, given the food security we are talking about, we might need to look at abiotic stress management more of intercropping, where one crop might take the excess moisture, other crop might use a less water. So you can have wet and dry kind of cropping systems you could develop there. And equally, there are also people talking about floating agriculture, especially in saline waters. So a lot of research is happening, but one of the challenges we see is the scalability aspect, which I will be speaking more about. How do we address and come up with the better management options on these abiotic areas where we work? To understand to this process, IWMI has done 9 stress related information sometime back with a funding from Asian Development Bank, and we have done a regional assessment more than 6 to 7 countries, looking at the percentage of drought, flood, cyclones, and looking after the vulnerability of those communities as well, which is at the end of the day what you would like to propose intervention. We need to understand not only the crop system but also the communities where they are looking at the food security challenges. So we did this assessment, and we are trying to release this atlas with much more knowledge products that are available. Due to limited time, I'm not going technical details of how we develop this product, but I'm free to reach over and share with you. And also there is a detailed research report is available. It's a joint collaboration with CCAF, where Paresh comes from later call today. He will be also speaking on the climate change, agriculture and food security. They are one of the collaborators of this program. So this is again ICAR support, where they look at current climate condition and look at the next 100 years, how that risk is going to emerge when it comes to vulnerability. So this is not a study done by IWMI. It's a great job done by institutes of ICR, where you can look at prioritization, what you could do much better in a regions like climate stress is already happening, what you could do much better in the next 20 to 30 years. This is where the science-based policy making will come into the picture, understanding the risk of climate using your climate scenarios information. So this is a very good early stock taking exercise, in my opinion, that will help the centers to adopt relevant interventions that one could develop. I would now go more into the specifics of how we can do much better job when it comes to, okay, we can do a national level climate risk assessment, understanding the abiotic stress, but I would speak more on the flood today because of limited time. We equally work on drought as well. So one of the proofing we feel is that we need to have a credible geospatial information in place. For example, understanding the climate, knowing the flood information. Even if you talk today flood data about India, it's very limited data is available. You can say there is a state that has a flood this much extent, but moment you go for a more geospatial information, there is very limited data is available. But today, a lot of good grid-based flood information, soil data, land use, all these informations are available. Then you could translate that into indicators like excess rainfall, deficit rainfall, understanding the frequency of the flood, knowing about the depth of the inundation and its duration, understanding the subsurface and the surface soil moisture, the organic content. You today have a lot of gridded data is available, knowing the slope direction of those landforms, irrigated area, soil type, and as well as the soil pH and etc. So what I mean to say, in this kind of time frame, we have extensive grid data is available, which is a very good development because of launch of series of satellites and the modeling tools that are publicly available, one could able to generate. And then we did a lot of multi-criteria decision tool and arrived at areas where you could look at specific crops like rice, suitability maps, how you could introduce a flood tolerant suitable, because it's not just you have a variety of rice is available, you cannot introduce just at the countrywide because you may not have that level of access to seeds even. So it's a question of where you would like to introduce, how best we can introduce. This is where this geospatial data comes handy to the policymakers or to the institutes like Abiotic Center, which are hosting this webinar. So we today have a lot of geospatial data, over 20 years of information, understanding the frequency of the flood, the depth of that, the duration of that. Large part of the countries where the receding flood is not less than 7 to 6 days, which we can see in large part of the Ganges, but there are areas where we have more than 20 days of inundation that happens, like in Brahmaputra, more in the floodplains, depending on the elevation and the slope condition. So this data, I believe, will also be helpful to the center. We are very happy to share all this data in the research where they lead on. Similarly, we have looked at the land use, the rain-fed areas. This is again ISRO provided the AWIPS-based land use, land cover information. Equally, as I was talking about the type of soil, its organic content, the pH level, all those data you could able to bring it into a unified database system, which will help us to prioritize the areas. This is what I was talking about, suitability class for flood tolerant seeds. So we have identified the potential where and how you could introduce, particularly of this particular variety. And this is a research in progress. We are not saying that it's 100% correct, but there is almost 30 to 40% of the area is quite suitable to introduce based on the methodologies what we are developing. Now, how do we go more proofing into that? This is where we have looked at collaborating with National Rice Research Institute. We looked at specific rice varieties like Sorna Sub 1 in flood tolerant areas, in drought varieties like Rajendra Bhagavat. We looked at how this can be adopted in regions in Bihar and UP. So we did a trial. So we have understood the seed features, how and this can be applied, and the crop advisories are very important for the farmers as well. It's not just about introducing a variety. We have to educate the farmers equally. How do they do the crop management as well? So we have a pest advisor tool. We have a plant doctor tool that can all help them to provide a needed information once they are introducing this crop. So moving on to that is equally important. Yes, we can identify the suitability. We could also identify the seed systems that can be introduced. But equally important, the agencies have to focus equally on the climate safety net as well. Beyond all this, there will be a degree of risk happens because no one knows the kind of a flood that happens, like it's already happening in large part of the country. This is where we introduce our flood insurance scheme, taking use of the same data sets and the knowledge products what we developed. The idea is use your water level, rainfall, flood extent, duration, and the remote sensing information. And of course, we work with insurance companies to come up with disaster loss information. And we worked over last 4 years, and we are in a position to say over 20,000 households are in the experience on this flood insurance product, not only in India, but as well as in Bangladesh as well. This was the first product we launched when the former agriculture minister, Mr. Radha Mohan Singh, was there. We prototyped this product in Muzaffarpur. Now we are expanding into several districts. And basically, we are making that data is transparent. So a lot of insurance companies are using this data, and it is based on index. So there is no field level based information that is required to collect. Everything through model data, IMD information, and the remote sensing based flood information. So this is again another form of stress management. If you want to mitigate, we also equally need to look at transferring those risks through the public-private partnership collaboration. The other area of I will leave this presentation to the audience. So there is a evidence study is done how this is useful within the overall abiotic stress management work we have done. Free feel to go through this link and learn about what we are doing there. And the second aspect is that I would like to focus more on bundling. This is where I was telling about understanding the biophysical risk is good, but then equally we need to relate that with the seed system, the climate information, because we cannot just look as a silo-based solution. It has to be a holistic management when it comes to agriculture resilience. So what we are looking at, there is a lot of technology trap the farmer is experiencing in recent years. One is their income is very low, their credit access is very poor, they are having a different degree of risk, and they don't want to take also those risk challenges because under the income deficiency or the available to agriculture input they may not have, so they are also not ready to take the risk. And that's where I see the low technological adoption as well. And looking at all this, we came with the aspect of how do we bundle these problems into more solutions oriented. So we had ventured with a lot of both public and private seed companies as a trial, and we have an insurance product for both floods and drought. We are providing advisory services over 1,600 households as a trial, and we provide package of practices on agronomy, fertilizers, and the water management. This is where I feel that it looks abiotic stress management as the next step of our efforts, what we are doing. So we look at before the event, provide the seed, provide the insurance and the advisory. When any risk has happened, the claims will be provided. And we also work with the Indian Institute of Water Management, providing the alternative crop management. So it's not just you get some claim and then you use that money wisely and next season you may not have any input. So we are trying to provide what you could better do with this excess moisture. So this is where early wheat varieties, helping the farmers to grow some vegetables. I'm not an agronomist specialist, but the colleagues in ICR are helping us to do this great work in Bihar and other part of Orissa and Assam. So we look at three-pronged risk management, improving seed, insurance, and weather alert, as I told you. And actually the good part we need to look at is the scalability side. Who is really going to gain on this solution? So we are saying that equally all of the private sectors like insurance industry, the seed company, weather advisory, as well as the government. Government cannot reach to each and every farmer. So having this PPP business model will really help them. The impact for insurance company is it is widely accepted because there are still a lot of challenges. Insurance is still not adopted, whether it's a Pradhan Mantri Fasal Bima Yojana or any other weather index insurance, because we need to build more trust, for which the product has to be really credible enough to support that. Seed companies also not really making a lot of portfolios that can reach to those communities. So through the insurance, there can be a good win-win solution for them. And farmers today are using a lot of smartphones, so educating the stress management is really important. So I feel a lot of telecom communication can come on board to provide this. It's not that we are telling today, it's a great job is done by the Ministry of Agriculture itself, along with IFCO Tokyo and other agencies are doing the great job. So when, however, we need to bundle that into the overall risk management. That's the message I'm trying to give. My last two slide is also looking at post-flood management. Yes, there is a excess moisture, and what are we supposed to do? So we have come up with if there is a crop that is flooded and the crop will be damaged right after the flood, what are the varieties of crop you could introduce and what are the flood management options we could put that into the farmer's hand, and how they could look at some are field-based activities they are supposed to do, and some are more on selection the choices of the crop. So for example, we introduced in a farm field that was flooded and the farmers were immediately taking up an eggplant or a tomato, and we have trialed this over 80 households in early years, and we have seen the farmers have increased the net income of over 250. Generally these areas they will wait until the post November, and then when the Rabi season start they will introduce a wheat variety. Rather we can bring them on board much early in the October itself or early September, depending on the stage and duration of the flood. So that's where we feel the role of geospatial comes into handy for diverse stakeholders who will be able to adopt this. So you can see more examples, like we are distributing more long varieties of seed varieties in Orissa. This is done in Puri district with the collaboration of ICR. A lot of evidences we have how post-flood management can also become an opportunity for farmers rather than just depending on receding the water and then start your Rabi season. My key message from all this discussion is that we need to know what is happening in the field, so that understanding the knowledgeable information from the stress management, whether it is I described the geospatial information, they are and the crop modeling data is very helpful. It is timely needed because for high level policymakers, they need to have science-based policies rather than on a collective measures what they can make a decision. So we need to increasingly put the pressure on policymakers on the use of science-based information. The second thing is all these evidences we are showing today has not been achieved to the scale where it is adopted at a countrywide. So we need to build more public-private partnership on the solution, and again it should be affordable to the farmers, and also it should be sustainable as well if we're talking about the overall risk. And last but not least, some of these knowledges farmers we are learning from farmers. Likewise, we also have to reach out to more farmers through the capacity building, and not just looking at the problem of agriculture from the stress, but also the overall value chain. Even if I tell them to produce eggplant or anything, there should be a buyer who should able to use that. So we need to also build that overall value chain. Otherwise, some of these solutions are only practical at a field level because they don't see income coming out of this. So more awareness, and we need to create more demand on this. With that, there are a lot of materials are available. I will leave it to the speaker. And thanks again for giving this opportunity. Over to you, Bhaskar.
Thank you very much, sir, for a very informative presentation, and coming to the key message of understanding the climate risk, looking at the scalability, affordability, and sustainability issues, and strengthening the capacities of the farmers. Now, at the end of this presentation, I request Dr. Sachin Pawar to pick certain questions from the chat box for the speaker so that we can address those. To Sachin Pawar.
Yeah, thank you. We have got few questions for you, sir, from the participants. The first question is IWMI working on fruit crops which are facing abiotic stresses, especially in semi-arid or arid regions of India?
Yeah, we haven't worked much on the fruit crops. As I said, we are only working on major pulses and cereals. For example, we have done studies on wheat. We have largely studied on rice and some vegetables like, as I told you about the tomatoes, eggplant or something. And again, as I said, I'm not really the expert of this field. This is mainly coming from the ICR Center of the Indian Institute of Water Management. I can connect you, put you in touch with them so that they can give you the appropriate answer for this.
Sir, the next question is, are the shape files of the hazard maps prepared by IWMI shared to work on various other platforms underlying them? If yes, whom to contact?
So please write to me. We can we have both the grid data as well as shape file. We can happy to share with you. Please do write.
Okay, so last question is, what are all the outreach programs followed to reach farmers?
Okay, so we have been, I mean, with the collaboration of our regional center for, I mean, in the Patna, we do each year the farmers Mela that's been organized by government of Bihar. Similarly, we are doing also in other states where we put a stall and explain them the insurance, the post-flood management, the bundling aspect, more translated to a language where farmers can really understand. But we don't say that we have done a lot of great work on outreach. But again, we partner with agriculture universities like PUSA, with ICR Center, who leads this support, because we are not a donor agency or not a development agency. We are research for development. So we work and associate with diverse institutions to do this outreach program.
Sir, we have got one more question, sir.
Sure.
How the drought can be identified through geospatial technology?
Yes, I think it's a, I mean, unlike other risk, drought is one of the complex indices that we can talk about when we say meteorological drought or agriculture or hydrological drought. We can potentially use geospatial data, whether it is access to weather information or vegetation condition. plenty of information is available in public domain. In fact, ISRO is also putting on an operational basis the drought information in a portal. So visit Bhuvan website or visit Manual Office Crop Forecasting, as well as our website. We are putting every 8 day the drought information for entire South Asia. So if you do not know the access, feel reach out to me over email. I can put you the websites where you could go and download the data sets.
Thank you, sir. Thank you for answering the question. Over to you, Bhaskar.
Thank you, Dr. In fact, there are a few many raised hands, and I encourage the participants to type the questions in the chat box because the time limitations may not allow passing on the mic to the individual attendees who have questions with them. Please send the questions from the chat box so we can ask the relevant speakers. From my side, I have a question, sir, which probably, in short, I should say that the bundling concept for the insurance solution. So this is one proposed solution, and on the other side, there's a low-tech trap. Do you see, sir, that data availability is a big question while even working out with the bundling concept during particularly extreme weather events?
Yeah, this is a very good question. I think increasingly this is where the partnership come into the place. When we started this implementation, the research institutions have access to, Borlang Institute of South Asia has access to a flood and drought tolerant varieties they have developed. But again, it is not available to the scale we can distribute to even a state like Bihar. So we need to find out more mechanisms of farmers itself is providing the germplasm, and they are being educated so that it's not just the private sector role is only to collect and sell the seed. We have to look at different value chain proposition on this if we are really going to look at the bundling. Having said that, seed side, insurance, I think they are improving their capacity when it comes to the reliability of the payout. I say like there are new guidelines have come in the Prime Minister Crop Insurance Scheme. Now, when the farmers don't feel there is a trust in the payout, the insurance company is supposed to provide a satellite-based verification information in addition to field data. So I think the core side is technologies can be addressed, but importantly is about the policies, because it's not just about these instruments are available, we can scale it up. There are, even at a state level, when you go, there is limitations of policy measures are there. Without any bundled buy-in, subsidies are not available. It will not have a scalable option. So we have to look at a lot more options of understanding the cost benefit models of all this topic what I am outlined to you.
Thank you, sir, for insights into this. One short question, which probably is the information on cattle management during flood. If any research information is available, one of the participants has asked about this.
What is that? Can I
information on cattle management during flood?
Cattle? No, I don't have that expertise to speak on that.
Thank you very much, sir, for all the answering all the questions and a very lucid and informative presentation. I now request our next speaker in the role, Dr. Rajiv Srivastava, sir. Sir, I guess you are able to hear me. You can unmute yourself, sir.
Yes, I can hear you.
Yeah, yeah.
Can I upload my presentation?
Yes, sir. You can share the slide till I introduce you to the participants. Praveen, you can provide assistance to Dr. Srivastava. To introduce our next speaker, Dr. Srivastava, sir, is known to many. Now, since while life, water is the life, we heard of water from Dr. Giraj Amarnath, sir. Soil sustains the life. So moving from water to soil, Dr. Srivastava is the right person we could find for geospatial mapping and the Abiotic area. Dr. Srivastava was working as a principal scientist and was head of the division of remote sensing application at NBSSLUP, Nagpur. Dr. Srivastava is a PhD in soil science and has a vast very vast experience of 37 years working as a researcher in the areas of remote sensing and GIS applications in soil resource mapping, watershed characterization, soil correlations, soil classification, land evaluation, soil spectral reflectance, and development of soil spectral libraries. He has more than 70 international and national research papers, 13 book chapters, and several technical publications to his credit. He has also guided MSc and PhD students and has taught courses in remote sensing and land resource management. So, and he has also received the Dr. J.S.P. Yadav Memorial Award for Excellence in Soil Science. He is also a fellow of Indian Society of Soil Survey and Land Use Planning, and has also been secretary of the society. With this very brief introduction of our next speaker, I request Dr. Srivastava to deliver his presentation on application of remote sensing techniques in geospatial characterization and mapping of soils for agriculture planning. Over to you, sir.
Thank you, Dr. Gaikwad. Good morning to all participants of the national webinar on abiotic stress management in agriculture. First of all, I would like to thank the organizers of this webinar for giving me the opportunity to present on the topic application of remote sensing technique in geospatial characterization and mapping of soils for agriculture planning. So I was informed by the convener, Dr. Bhaskar Gaikwad, that many participants are researchers and scholars, and they are not very familiar with the remote sensing technology and how the soil mapping is done. So in this presentation, I will just very briefly discuss about what is the basics in remote sensing, what are the satellite data, and then how the soil mapping is done, and then how the remote sensing can be applied for mapping and preparation of soils. So this background, I just want to present that this is the basic definition of soil science, that remote sensing is the science of deriving information about an object or phenomena through analysis of data acquired by a device that is not in contact with the object or phenomena under investigation. This is the basic definition. And as we know that every object reflects or scatters a portion of electromagnetic energy that is incident on it depending upon its physical and chemical properties. In addition, objects emit radiation depending upon the temperature and emissivity. And this reflectance and emittance of object at different wavelengths follow a pattern which is characteristic of that object and that we call a spectral signature of that object. And proper interpretation of a spectral signature leads to the identification of object. This is in this figure, I am just showing the major spectral signatures of vegetation, red soils, black or red, and water. This is the special spectral signature of the soil. And as we know that atmosphere is not transparent to all type of electromagnetic radiation, and many of the radiation, they are absorbed in the atmosphere by the ozone layer or carbon dioxide and the water molecule. These are the regions, atmospheric region, that with spectral wavelength like 3.3 to 0.75 micrometer region that is transparent, and there we can use the remote sensing technique. These are the wavelength region in NIR, MIR, thermal, and microwave. Then the characteristics of remote sensor, mostly the data from the remote sensor, they are characterized by their spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. And the spatial resolution, it refers to the capability of sensor to discriminate the smallest object on the ground. Finer the spatial resolution, better the image quality. And the spectral resolution, it tells about the number of spectral bands or channels and the bandwidth from which the data is recorded. Radiometric resolution, it indicates the ability to distinguish the final variation of reflected or emitted radiation from the different objects, and it is mostly represented as bits. Temporal resolution, it is the ability of satellite to cover the same area on the Earth's surface at regular interval. Now, I will just discuss slightly in more detail the spectral resolution. The spectral resolution describes the ability of sensor to define fine wavelength region, and the finer the spectral resolution, the narrower the wavelength range for a particular channel or band. Now, the advanced multispectral sensor, also called hyperspectral sensor, which detects hundreds of very narrow spectral bands throughout the visible, near infrared, mid infrared region. And their very high spectral resolution facilitates the fine discrimination between different targets based on their spectral response in each narrow band. In this figure, I am just presenting the average data, average census data of Chamarajanagar, Nagpur, Chamarajanagar of Karnataka district. And average, this is a airborne visible infrared imaging spectrometer data, and NG stands for next generation data. This is a data that is recorded in 380 to 2510 nanometer region, and it is having a sampling interval of 5 nanometer. That is the bandwidth, and the spatial resolution of the data is 3.7 meter, and it covers nearly 425 bands. And if you just see the spectra, when a spectrum from a single pixel in a hyperspectral imagery is displayed, it appears like a spectrum measured in the spectroscopy laboratory. This detailed pixel information spectrum can provide much more information about the surface than available in the multispectral bands. So we are getting almost the similar what we are getting in the laboratory. Before proceeding further, because when we are discussing in remote sensing, they are new people, they are not very familiar with the band, channel, color, and FCC. So I just try to explain that reflectance of any objects from a narrow wavelength region is gathered and stored in channel. Channel and bands both are the same thing. And we can combine and display channel information digitally to using 3 primary colors, blue, green, and red. These are the 3 primary colors. And depending upon the relative brightness of each pixel in each channel, the primary color combines in different proportion to represent different colors. So because of the confusion, because we have a blue, green, red band also, and we have a blue, green, red. So this creates confusion among the those who are new in remote sensing. So never confused with the blue, green, red band. These are the primary colors. We can assign any color. There is a standard false color composite. Imagery is generated by assigning red color to infrared band, green color to red band, and blue color to green band. By assigning, because as we know that infrared doesn't have any color, we are assigning red color to infrared. And this is called the standard false color composite. I will just show you the images of the list 4 data. This is the band 2 data, which is a green band. Band 3, it is a red band. And band 4, it is an infrared band. So if when we are displaying the individual band, they appear in black and white color. That is a images. This is the water bodies and how the different objects appear. If you just concentrate here, then you will see that wherever there is vegetation, it is giving relatively lighter color as compared to red band, which is a red band because of the absorption of radiation. And this is the infrared, which is giving the highest reflection. When we assign the infrared a red color and red band to a green color and green band to a blue color, we are getting this false color composite. So this false color composite, because in vegetation reflects more in the infrared region, and we are assigning red color to infrared. That's why in false color composite, we always get vegetation as a red. Now, you will see the application of remote sensing application in soil mapping. And before proceeding to soil mapping, we will just discuss how the soil maps are prepared. Basic concept in soil maps are prepared mostly taking into consideration the factors of soil formation as outlined by JNE 1941. And the factors of soil formation are climate, that is CLROPT, climate, topography, relief, living organism, and material and time. And we use the soil landscape model. Soil landscape models are the natural terrain resulting from 5 factors conventionally stated in the functional equation of JNE. And the soil landscape unit has a recognizable form and shape on the Earth's surface. And the landscape unit, which we call, which is similar to landform, but it is more narrowly defined. And USDA has defined 5 orders of soil survey. And first being the very intensive, and fifth being the very extensive. And first order soil survey, which is generally, and the scale, because whenever we are talking about the soil map, we talk about the scale, because as per the scale, the kind of mapping unit changes and the information content in the map. So first order soil survey, that is having a more intensive soil survey, more ground truth is required in this, and the map units are mostly consortium, that is the individual series or some complex, and this is mostly done on 10,000 to nearly. And second order soil survey, that is 12,000, 25, 31,000 is scale. Third order, there's the extensive type of soil survey, and fourth and fifth order, that is very explorative soil survey, fifth order. And this is mostly done on 1:250,000 scale or 1:10,000 scale. And mostly the kind of mapping units are association of families and higher level. So these are some of the data, Indian remote sensing satellite data, which are used for soil mapping, IRS-1A, 1B, 1C, 1D, and they are what is the pixel size of the data products, and what are the bands available in that particular satellite. Now I'm just displaying the IRS-PC data of different scales, like AWIFS, Advanced Wide Field Sensor, that is 56 meter resolution. The same area I'm displaying it on LIST data, which is covering this, and this 4 data, that is 6 meter resolution. As we having higher the resolution, more is the information content in the data, and you can enlarge it to a more extent. But when the spatial resolution is lower, 56 meters, having less information as compared to the high resolution data. Now I'm just displaying the IRS-P6 list for FCC of a area of a village. You can see that the FCC, this data, list for data, can be used for cadastral level soil mapping. Cadastral level information, what is there in the field, which we are seeing in this data. And when we are doing soil mapping, it is very important to know how much area pixel are there in that. Like Landsat MSS data, multispectral Landsat data, that's having a resolution of 50 meter, and it is having, if you just calculate it in terms of pixels per hectare, it comes to 1.56 TM, that is 30 meter. It comes to 11 pixels per hectare you are getting. And if you just see the IRS 1C, 1D list 3 data, you are getting 18, and list 4 data, you are getting 296 pixels per hectare. When you are going for a large scale soil mapping, you need a high resolution data like list 4, where you can get a more information about the area. And another important thing in soil mapping is the selection of optimum season for data for soil mapping. We have just tested in our basaltic terrain the remote sensing data of October, then January and April. With the list 3 data we have just seen, and we just evaluated, and we found that March and April data, season data, are best for soil mapping in this basaltic terrain because of relatively more exposure, better contrast we are getting in the data for delineation of different landform units. Based on the National Bureau of Soil Survey has developed soil resource map of the whole country, different states in the country at 1:250,000 scale, using the satellite data of Landsat and IRS data in conjunction with Survey of India topo-sheet of 1:250,000 scale. And we have, using the 3-tier techniques we have used for mapping. That is the first part is the image interpretation for delineation of landform units, and ground truthing and soil analysis, and developing the physiographic relationship. And third is cartography and printing. These maps, which are developed on 1:250,000 scale for different states, they are ultimately published on 1:500,000 scale without any cartographic generalization. This is the soil map of Maharashtra, which is having nearly 358 type of soil units are there, and the soil map shows the association of soil families, different soil families in this area. This is by combining the states of 250,000 scale by cartographic and categoric generalization. We have developed the soil map of the whole country on 1:1 million scale. And this map has a soil map of 1:1 million, has 1,649 soil mapping unit as association of soil subgroup. And these are the soils which we are getting as per taxonomy. The area under the incepti soil is nearly 40%, in soil 28%, alphy soil 13.5%, and moldy soil they cover nearly 0.4% of the total geographical area of the country. We have also prepared the soil map of different districts. 76 districts have been surveyed and completed on 1:50,000 scale. Here we have used mostly the history data of IRS 1C and 1C data. Using the history data information, we have just prepared the soil map on 1:50,000, nearly 76 degree, and these soil map which are prepared on 1:50,000 scale have association of soil cities as a mapping unit. Then this is the flagship program of the Bureau, which is being conducted on 1:10 land resource inventory on 1:10,000 scale for agriculture planning. Here we are using the IRS list 4 and AutoSet merge data for mapping the soils on 1:10,000 scale. Nearly 292 blocks of have been completed, and 65 blocks have already been submitted. 214 blocks survey has been completed, and 14 blocks the survey is ongoing. So these are the information available, and in the geoportal, Bhumi geoportal of the National Bureau, and anybody can see it. And the data in the form of shape files can be shared with the after getting the memorandum of understanding with the analysis. And this is the soil map of a village level soil mapping using the information we have developed, where we can get the cadastral level information about the soils of a village level. And these are the mapping units. This data has information about the depth of the soil, what is the drainage, what is the color, what is the texture of the soils, and what type of slopes and surface texture, erosion, and the stoniness. So these information can be derived through the soil map of high resolution data. And if you just see, when we have just presented that soil map at different scale, as we are going from small scale to large scale, we are getting more information content in the map is increasing. Like this is the area of in the Nagpur area we have just conducted this, the information about the soil, and when we do it on 1:25,000 scale, this is the information available. As we are going for 25,000 scale, then we are getting 12,500 we are getting, and 5,000 scale means very high intensity. Without using the data, we are getting more information content. As we go from small scale to large scale, the information content in the soil map increases. I am just presenting here the mapping of salt affected soils, which was conducted by LUP in IGP areas. In IGP areas, the discrimination of salt affected soils and sandy soils becomes a great problem in mapping. This is the IRS 1B list 2 data of a ETA district. And you just see, because of the appearance of salt affected and sandy soils together, it is very difficult to separate it out. This separation has been done using the Landsat TM data. When we are using the Landsat TM data, because this is TM band 6, this is a thermal band, which is based on temperature. So because of if you just know the genesis of salt affected soils, the salt affected soils in IGP area, they are formed of the boiling groundwater, when it is moving through evapotranspiration, and it is deposited on the surface. Because of this salt and precipitation on the surface, they are relatively cooler as compared to sandy soil. So if you just see, these areas which are appearing lighter in color, they are the sandy soils, and this area, these are the salt affected soil because they are appearing darker in the thermal band because of the low temperature, and these are the dry soils. So once you are interpreting the false color composite of that particular area, you are having both sandy soils and salt affected soils, and when you overlay it over the thermal band, you can identify which are the salt affected soil and which are the sandy soil. Now, another field is the reflectance spectroscopy and rapid characterization of soil quality attributes. For this, you need to develop a soil spectral library. Soil spectral library is the most important thing. Soil spectral library refers to the systematic collection of soil reflectance data of soils whose properties are known and that can be used as a reference to predict the properties of unknown soils based on soil reflectance data through modeling chemometrics technique. This is the laboratory setup for measuring the spectral reflectance of the soil. And these are the spectral reflectance of the soils which we are getting, number of soils we have done it, and how the spectral reflectance of different soils varies. And these are the modeling. Modeling we can do it because the spectrophotometers which we have that measures the spectral reflection between 350 to 2500 nanometer with 1 nanometer sampling interval. So this data is having very high resolution. So there is a repetition of data. So data reduction to resampling of raw spectral data at every 10th nanometer, 350 to 2500. And then transformation of spectral data through derivative transformation. There are so many techniques are available, and we can just do the transformation. Then removal of noise bands. Always there will be some noise band. So 350 to 350 to 380 nanometer, this creates a noise. So that has to be removed. Similarly, at 2460 to 2500 nanometer, there is a noise band. And in between also at nearly 970 to 1020 nanometer, there is a noise band because of the change of spectrometer. So these bands have to be removed. Then we are doing the subsetting of the data set for calibration and evaluation, developing the spectral models by calibration technique. You can use different calibration technique like PLSR, principal component regression, PCR, or random forest, or artificial neural network, or support vector machine. Different models are available, and that you can use. And then the testing of the accuracy based on the R square, RMSAP, and RPD. This is the transformation. This is the data which we are getting through measuring the spectral reflectance, and we are just transforming into first derivative so that the effect of scattering due to surface scattering is reduced, and we are using this first derivative for calibrating with the soil properties. And this is the spectral plot of measured and predicted values of SOC in IGP soils of the area, where we have 800 samples we have collected, and of that 60% samples we have used for calibration, and that and 40% samples we have used it for validation purpose, and using the partial least square regression technique. This is the regression coefficient of the PLSR model, and we are getting nearly 0.6 R square, and in case of validation set, we are getting R square is 0.81 with RMSAP of 0.11 and RPD of 2.3. This is the spectral plot in the validation data sets of salt affected soils. There also we have got very good relationship between the laboratory measured spectroscopic based measurement, and we have got a very good relation for EC, then calcium, magnesium, sodium, and chloride in the solution. And this is the summary statistics of a spectral model developed in case of salt affected soils. We have got very good relation with the EC, then such. explained in the previous slide. And another field is the digital soil mapping technique. And here we are using the average NG data for mapping of soil attributes. This is a hyperspectral remote sensing technique, average advanced visible. And still the work is in infancy in the country, and a lot more have to be done. This is the methodological framework for which we have developed it using the average NG data, then harvested them and the field work. In average NG data, the data processing, removal of noise band, then spectral reflectance image, just convert into a PCM because 425 bands are there, and just to handle that, we have just done the principal component analysis, and we have selected 3 PCS, and that covers nearly 85 to 88% of the variability in the different bands. And then similarly for partition dam, we have derived different terrain. We have done the terrain analysis to derive different environmental covariates like map, elevation, slope, plant curvature, profile curvature, aspect, stream power index, then topographic hardness index, and DVI. And we have extracted the information, and then we have collected the ground truth information, soil analysis, organic carbon, pH, etc. And then we are relating all these parameters and developing the spectral models, building the multivariate regression models, and we have tested the residuals. If the residuals are auto-correlated, then we go for a regression tree type of rigging. If it is not auto-correlated, then we are doing the regression modeling, and then masking of the vegetative. So this data which we have used it and developed the spectral models. The modeling is giving the R square of 0.48 for 43 for organic carbon, then available P. So this is because we have done it with limited data, only 48 samples we are using that particular watershed. So still work is going on. I just wanted to just share it, and this is the map of SOC, then available P and available K, which we have developed through the digital mapping technique using the average NG data. The way forward, as I think, we need to develop a cost-effective, because you know that soil survey and soil mapping, it is very costly and time-consuming process. There is always a need to develop a cost-effective and time-efficient techniques using geoinformatics and pyrometric techniques for precise mapping of soils at different scale for monitoring this data source. Because it is very costly affairs, and so there is always we have to work on it, pyrometrics and using these techniques, so that we can do frequent monitoring. Developing digital soil mapping technique of predictive soil mapping using geostatistical technique, remote sensing, and GPS GIS. There is a need for developing a robust soil spectral library so that we can develop a robust soil spectral models using different machine learning tools like PLSR, ANN, SVM, learning forest, quick and reliable prediction of soil property, soil quality attributes. And another last thing is the capacity building. Capacity building is also important in the field because very limited people there. So there is always a need for developing a capacity building at every institute to take a work in this direction. Thank you very much. I'm finished.
Thank you very much, sir, for starting with basics and coming up to methodological framework for digital soil mapping. I thank the speaker very much for having this topic explained in a lucid manner. I will take a couple of questions from the chat box. We have got one question from, so you can unshare your screen in this case. So that, we have got one question is from Mr. Pabitra Santra. So he's asking what should be the best approach to develop the digital soil map product of the whole country as specifically doing for the whole world.
Can you repeat it? I could not actually.
He's asking what should be the best framework to develop soil map for whole country, similar to what ISRIC has been doing for in case of world map.
No, I could not get it actually.
Okay. ISRIC has developed certain maps. What India should be doing to develop similar maps?
ISRIC.
What is the framework?
ISRIC actually they have done the soil mapping on very small scale. Soil map is there. We have already developed the soil resource map on 1:250,000 scale, which is having of the whole country, and 50,000 because this takes a lot of time. So we have developed better map as compared to ISRIC. ISRIC information of the whole is a very coarse information, and we have developed already developed SRM soil resource map on 1:250,000 scale of the whole country, and we are going for a large scale soil map where the soil we will be having more detailed information about the soils for village level planning of the country.
I hope for details, Mr. Prabhatra would probably contact Srivastava sir for further details on if ISRIC methodology he specifically wants to use for the Indian soil mapping condition. The second question, sir, is this hyperspectral spectroscopy has shown good correlations with Ca, Ca2, sodium, calcium, phosphate. What about the dynamic nature of the soil? How frequently it needs to be mapped to get the dynamic nature?
In spectroscopy, if
yes,
you spectral data, because hyperspectral data is because satellite hyperspectral data like Hyperion is available now. It is discontinued. Our country is having a high-side map, hyperspectral imager, which is a very coarse resolution. That is on the data is available having the 500 meter spatial resolution. So this information in future we are going to get better high spatial resolution data for data in your for deriving the information about the quality of soils. And in the laboratory we are doing it, measuring the reflectance of the data collected from the samples. So how frequently you are getting the data from the field, it depends upon that. So measuring soil reflectance hardly takes you can just relate it and predict different soil properties from the hyperspectral data.
Okay, sir. Yes, sir, you are audible. There are several questions in the chat box I can see, and also on the YouTube handle also we are getting questions. However, due to paucity of time, we'll take this question later on at the end of the session, or I request the speaker to address specifically those maybe through emails in the case we don't get an opportunity. Thank you very much, sir, for gracing this occasion and also presenting some basis to coming up with the methodology framework for digital soil mapping. Thank you very much, sir.
Thank you.
The soils are sustaining the life. And a major area for mapping. We have got the next speaker from Indian Institute of Soil Science, Dr. Pradeep De, sir. Dr. Pradeep De, sir. Can you listen to me, sir? Yeah.
Yes.
Yeah. You can share your presentation in meantime, sir. I will be introducing you, sir, to the participants. It's a privilege for me to introduce Dr. Pradeep De, sir, who is presently working as project coordinator of All India Coordinated Research Project on soil test crop response. He's also principal scientist at ICR ISS Bhopal, Indian Institute of Soil Science. His research work is specifically on soil fertility mapping, enumeration of spatial variability of affected soils, nutrient and crop management in watersheds, carbon sequestration and conservation agriculture, root pruning, fertilizer application, in situ moisture conservation techniques, and multi-tier fruit-based cropping system model, and it's linked to wide system consideration. Dr. De has experience of participatory on-farm research on sugarcane-based cropping system. He has contributed more than 400 publications, including 138 research paper, 14 books, 30 book chapters, and many more. He has won 2 gold medals, 6 scholarships, including World Bank Summit scholarship. Also, Dr. D is also fellow of several scientific societies, including West Bengal Academy of Science and Technology, Kolkata Indian Society of Soil Salinity and Water Quality, Karnal, fellow of Indian Academy of Horticulture Sciences, and he has also received several peer recognitions to his credit. And his, he is also the recipient of Social Innovator Award by the World Bank UN. So this is very brief introduction about Dr. Pradeep Dey, sir, and I request him to deliver his presentation. Over to you, sir.
Okay, thank you, Dr. Bhaskar. Respected Director, Dr. Pathak Saab, Dr. Bhaskar, and esteemed panelists and delegates. So this particular welcome to this particular presentation. Is the screen viewable to everybody?
You're audible, sir.
So this GPS and GIS-based soil fertility mapping, the stepping stone towards precision agriculture. This is the particular topic, and these are the outline of presentation. So I'll be briefly covering what we have done at ISS Bhopal, and then through particularly a mega project funded by DSC and FW, about 10 crores project. And then also we have got ECRAF, ICR collaborative project. Little bit I'll be touching because already soil remote sensing and all everything covered very nicely by Dr. Srivastava. So, but I will be touching only the MIR portion that we are doing here, mid-infrared spectroscopy, and then how these maps can be used for say in the practical field like customized fertilizer development or precision nutrient management, and in the decision support system that I will be briefly covering. So quickly I will go to the presentation. So this is the productivity challenge that almost known to everybody. Just to keep the setting, this is the rising food consumption due to growing population. We need more food, and then climate change and agriculture water resources, water availability is another driver, which is red driver, and then less arable land per capita, less arable land due to rapid urbanization as well as climate change. So these are the factors. Apart from that, now we have the pandemic, so that is another factor that is there. And these are the Indian share of world population: 70% water, 4% land, 2.4%. So to manage through these limited resources with our vast population amidst pandemic, that is very important. And sometimes you know that this mapping is a kind of pandemic resilient kind of activity, because many times if you have a good map, or you can have better peto transfer function from already available data, then you can go and without physical contact or to the places and then predict. And as you know that as FAO's main motto for Glosalan is that if you cannot measure soil, you cannot manage the soil. So at least some measurement is required, and mapping gives one of the tool to measure without going to the particular place physically. So this is the geoinformatics that we use, that pattern relationship and processes that are interlinked together to have the GIS based mapping, GPS and GIS based mapping. And aim is to assessment of plant nutrient status, diagnose suspected nutrient imbalances, monitor effect of management of nutrient status vis-a-vis soil fertility. Then to some extent we also assess the toxic nutrient in the element, toxic nutrient element or heavy metal pollution, and then provide the basis for making fertilizer recommendation through this mapping. So these are the broad flowchart that we followed during our GPS GIS based soil fertility mapping of DSCFW project. So I'll be covering very quickly, but little bit of everything. So these are the four main, that sampling process. It starts with sampling, simple random sampling, of course, it is very good, but you need to have all the data of total population, and then you have to draw by randomized the computer generated random number or through seed method, and then you have to do. So this is very cumbersome and it is very almost not possible. So we have to go for either this type of cluster sampling or stratified random sampling or systematic sampling. So what we followed is, it is called, if you put together, it is a kind of random stratified sampling method where we took district as the highest data, then we segregated in different blocks, east, west, north, south, and in fourth quadrant, and then 15% of villages of the district, total district, that is randomly selected in fourth quadrant, and then those district, randomly selected districts, each district, that 15% villages are actually sampled, and in each village 6 samples are actually taken, GPS based sample, and 2 sample from resource rich farmer, 2 sample from medium resource farmer, and 2 samples from poor farmer who are having resource endowment capacity very less. So background behind this sampling, what we did is, actually we assume that farmer who are having more resources, they are having more, they are more capable to put more resource in the field, and with time their field may build up in fertility. So more than nutrient mining, so that there is a chance. Of course, there are absentee farmer there, and those actually some aberrations already there that can be cropped up, but usually this assumption works in Indian condition. And then through under GPS, after GPS based collection of sample, actually 1% sample was, by giving a number, it was sent to ISS Bhopal, and then that was checked in the April lab of ISS Bhopal whether that total sample what was drawn by the centers, that is working well or not. So 20 centers across India, they worked for this project, and then there is a cross verification, and if there is some problem, then it was referred back and whole lot has to be analyzed again. That was the thing. Then under ArcGIS environment, we did that under interpolation method of rigging. So just quickly, I am going through this, and for I was told that to some extent for the students also some things should be there. This is just for student. If we put any type of, say, there are so many models available, spherical model, circular model, then rectangular model, whatever model you use, 8 main type of model we mainly generally use. Then we keep 3 things in consideration. One is nugget value, that is the starting point of, say, your model. So, and another one is where model flattened off, that is called seal, that is under y-axis, that range, and where model flattened off, that is under x-axis, that is called range, or it is also called lag distance. So these 3 things are very important, and nugget is a, you can say this is a kind of noise. The less is better, but we cannot avoid total nugget value 0. Ideally it should be 0, but usually you will get some value, but it should be within measurable limit, within, say, a kind of say acceptable limit. So yeah, the less nugget value is always better. Also, one should understand that there is a called a, apart from that lag distance, that h value, what we consider that u particular sample value and u plus h, that is after the lag distance, what is the value. After actually that lag distance, autocorrelation assumes 0. There is no correlation of the data. So that's why we remove that. That is why curve flattened off. But there is a kind of lag tolerance is also there. And this lag tolerance, within that, every sample is actually taken same. So this is a kind of limitation of the model, but we have to keep the lag distance minimum so that our prediction is better. Then we scrap from the, so all these things are done actually from the in the GIS environment, but with the after plotting and after this high, medium, and low value of the each layer, we scrap from the village boundary from the district boundary, and we arrive at maps. So this is in totality the different methods. I will give this thing in a kind of write-up. It is already there, so that will anybody can refer. I will share it in the chat. Then we came out with this type of map. Earlier we had nutrient index-based map, and as you know that index-based map is 3 times of high number of high level of nutrient, medium level is multiplied by 2, and low level is multiplied by 1, and then total number of sample is high, medium, and low numbers. So this is called nutrient index, and through index method we arrive at this type of map. But these maps, is there some better way for that map? We thought of that, and then this is the one that was actually done later on. So all these points actually, these black dots are actually that 6 sample per village, actual sample. So each dot represents 6 sample, and there are so many samples are there. So that was taken, and that was used for coming out with the maps. These maps are good in the sense that if you take on the adaptive management tool, this is just indicative that alternative 1 or alternative 2, which one is better, you can arrive at. Also, you can go back to any point, and then after the 3 to 5 years, and then you can ascertain whether the things are sustaining or aggregating or increasing or degrading. So whether there is mining, or whether it is sustaining, or whether there is more mining, or whether there is aggregating, means accumulation of nutrient. So that type of thing we can assign, we can arrive at, and we can cut down on fertilizer requirement subsequently. So these are some maps of Rajasthan. So 175 agriculturally important districts are covered in this particular project, and that was mapped. And these are micro and secondary nutrient map, sulfur, zinc, iron, then we have copper and boron. So these maps, but grid system in SHC, that is another thing. Usually everybody asks how it is arrived at. What actually was taken is 10 hectare for rain-fed and 2.5 hectare for irrigated. Then how we arrive at a particular point in the map, how we draw it, mainly for the students or initial level researchers. So we know that if you have 1:4,000 map, if you want to prepare, that means each centimeter on the map is 4,000 centimeter on the actual field. So that means 1 centimeter represents 40 meter in this map. So if you take 10 hectare, so 10 hectare means 10 into 10,000, that is 1 lakh square meter. So if I take as a uniform square meter, it will happen that 316.227, that is 316.22 will be each side of that 10 means 1 lakh square meter, that 10 hectare area. So if you 316 into 316, if we do 317, then it will encroach another speed. So we cannot go upward. So what we did, we have to take it to 316. Now, if we divide 316 with 40, that is 1 centimeter is 40 meter in actual field, 4,000 centimeter is 40 meter. So 316 divided by 40, it comes to 7.9. So that time we did a lowering of the scale, that is 316.22, we take 316. Now what we did, 7.9 we take as 8. So it is mostly moderated. So it is coming. So 8 centimeter into 8 centimeter, if we take in actual your cadastral map of 1:4,000, then you can make a grid of 10 hectare. Then if you take for rain-fed system, that is 10 hectare for irrigated 2.5. Just if you divide 4, so 2.5, 2.55 to 7.5 and 10. So like this, each 8 centimeter will be ultimately, it will be divided. So 4 each side. So 4 into 4 will be your 2.5 hectare grid. So wherever it is rain-fed, you take 8 centimeter. Wherever it is irrigated, you mark as 4, another equal square. Your grid is ready from cadastral map of 1:4,000. So if it is 1:4,000, you need 4 centimeter, and this is actual field distance. Actual field distance will be same, only this length in the grid map will be different. So 8, it will be less 4. So 1 is to 16,000, it will be 2, 1 is to 32,000, it will be 1 sample. So this is mainly cadastral map. From cadastral map, if you arrive, so 8 centimeter into 8 centimeter, you just start from one boundary, draw equals 8 centimeter line, and then from top again you draw another line, and each equal perfect square you take whole sample, another square which is boundary of the district you can take 2 3 and then according to area, and then take sample accordingly. So ways to proceed. Story so far is we had GPS based sampling. We also had used GIS environment. But is it the best method? That is the question. Grid sampling, of course, is an unbiased method, relatively quick method, and mostly it is followed. Internationally, it is also used. But it is also there are two types, that is grid cell method and grid point method. We make out with checkerboard type of map or smoothed map. Usually we go for grid point method now, and we arrive at smoothed map. But whether this is the best method, there are some shortcomings also in this method. Main shortcoming is there is no unanimity in arriving at grid size. We had separate studies in STCR where we have seen for each nutrient, for pH, even for very long distance, if the soil is color is almost same, you can draw only 4-5 sample and that will work. But if you go for phosphorus, variability is very high, you need to drop much more. So there is a difference. Another one is unduly biased result for localized irregularity that arise in grid method. That is another problem. But we tried another thing in this GIZ, the German funded project with NABARD is the main nodal agency of India. We had in these states, that is Maharashtra and this Madhya Pradesh. In Madhya Pradesh, this is Balaghat and Mandla. These two districts they are covering. In Balaghat, we did this thing. I am in their this advisory panel, national advisory panel. Then we did this through this. This is called participated direct sampling. If you look for literature, also detailed study in statistics, you will find that there is a system called participated direct approach, where you can involve community. If you have to have a very good, means farmers know when their field where water is stagnated, in their field which particular patch is red soil, which particular undulating land, upper reaches it is usually red soil and lower reaches it is usually black soil. Then if you involve farmer and then do a community involved participatory sampling, which is direct sampling, then one thing is it is very easily it can be taken up and can be implemented also very easily. And this type of clustering we can do in this case, and this cluster, each cluster with a high phosphorus, nitrogen is almost low to medium maximum. It is not even medium in many cases in India. But only major difference is, except in Tarai region, you can say, and 2-3 other region, we have seen nitrogen is never high. So nitrogen is low to medium, and then phosphorus and potassium, we have graded different. And then if we draw this type of cluster, and each cluster with the same type of color, we can have same management practice. Also, we could segregate districts based on this GIS GPS-based soil fertility map, and it could be used for macro scale soil fertilizer. This one, your distribution. This type of segregation we could do, like for example, in Kerala, for textbook knowledge, Kerala is acid soil, red soil. It is prefixation is very high. That is true. Kerala is 100% literal state. Extension machinery usually from north to south. If you go, extension machinery is more stronger in south. I have seen. I have centers throughout India. 25 centers. I have visited all centers several times. Usually it is better, but even then, and there are mostly many farmers are absentee farmers. They are plantation crop farmer. They give lot of input. They are having resource rich farmer. what happened, phosphorus, they have applied a lot of phosphorus, and 20% use efficiency, 80% goes to this either fixed form or unavailable form. With time, those phosphorus become available, and now phosphorus, this Kozhikode, Ernakulam, Thrissur, Alappuzha, these particular districts I have seen phosphorus is very high. So if you go for textbook knowledge and if you just copy what was there in earlier and then copy the same thing, you will arrive at this phosphorus should be recommended, but it is not so. So this type of, we could segregate district with high potassium also, we could segregate district with high sulfur and with high zinc. Even so much so that, when Ludhiana PAU, when the cultivated soil that project started, zinc application was very much essential for Ludhiana. Now our center at PAU, STCR center at PAU in this project, it was separate project upward. They found that Ludhiana now it is zinc is not so deficient. So that is coming. Majority field zinc because 25 kg per first of all 25 kg zinc sulfate in 3 years they were recommending. Then each year in rice, then they have given in wheat itself. So rice wheat each crop ultimately it has grown upward. So it is. So this type of also it is required in vernacular language in each language, even in tribal language like different, very rare language, we have translated and we have segregated this idea. Then spectral signature for soil analysis, only I will restrict to MIR part and NIR. So MIR, this particular equipment we got from XRF, and this was actually, we have seen that particularly pH, EC, organic carbon, these three things and clay content. These four things in physical side clay content, these four things can be, we got very good correlation, but we have some issues with phosphorus and potassium, not so far. So this type of characteristic spectra we can derive and we can arrive at which particular height that is more sensitive, which particular spectral band, and then from there we can arrive at we can generate a library, and from library we can arrive at how much is the nutrient content for a particular place. So this type of thing we could generate, and also it was possible to arrive at segregating potassium bearing mineral rich soil, different type of soil, particularly different potassium bearing mineral that could be having different type of peaks in a particular band. That was also possible to do with this. And then another one is X-ray fluorescence spectroscopy. This is in nascent state. We, for of course, for total elemental analysis, this is very good. For availability, we are still doing some analysis and we'll perhaps with time will come up. But for heavy metal, where there is a different period transfer function, like for total is having a definite correlation with available, there it can be very easily used even now. Then ion sensitive electrodes for selectrode, this is also one study is going on at our institute. So ISFET mainly that is being studied in this place, and we are trying to develop the library again, which is still in nascent state. Also, all the data has been handed over through one MOU to NBSS LUP, and that was incorporated in the Krishi portal that we are told, and director of NBSS LUP and ISS. Then that was a joint MOU, and we did, and ICR also adopted open access policy. So through them, it is also possible to access. And these 6 hub repository, mainly this data is available, and I see a geo portal here, all georeference data that is available in ICR. Another one we could find that this particular site is good, and there whatever we have seen that for particularly rubber they have done, and this particular site if you visit and if you have some data to be analyzed for rubber growing areas or adjacent areas, then you can visit this RAPSIS. So this particular site we found useful. One can go for it and then look for your data if you have something to say take from them. So this particular mapping can be interlayered in a GIS-based environment, and that can be used for both dual purpose of balancing nutrient use as well as arresting land degradation. And we can arrest land degradation in terms of fertility, particularly in the phase 1 where it is very slow slope or low slope. The slope is very narrow, means slow, or very, if you make dy by dx, then here slope is very less. But here you see in the phase 2, slope is dy by dx, slope is very steep. So once we arrive at phase 2, then it is very difficult to arrest the soil degradation here in terms of fertility. So that's why mining will be very high and ultimately it will be petered off in the phase 3 while it is stabilizing phase. So it is possible to arrest in the phase 1 at least by having some analysis through this particular GIS and GIS-based soil fertility mapping. Another use we could find that with industry, two industries, Indogal fertilizer, and that is in Indogal fertilizer is in Jagdishpur, and also we have given this thing to another one fertilizer company, that is Coromandel. So they have found that this can be used fruitfully for arriving at customized fertilizer. First, you draw what is the fertilizer based on fertilizer availability based on mapping. Then from STCR recommendation, you arrive at nutrient ratios, N by P, P by K, N by K, and then what is the nutrient ratio that has to be taken for a particular crop based on STCR, say for a particular target, and from there we could develop customized fertilizer. And with little tweaking of different nutrient ratios, almost here application is less, purchase price will be more. So it is actually by balancing, total price will be more, but almost same amount of money has to be invested, and we can arrive at better yield and partial factor productivity. Also, STCR and these fertility maps that are included in Government of India GIS, this soil health portal. And now we ourselves has developed another online system for Tumkur district on a study basis, and now for whole of Karnataka government has funded, and now we are doing that linking with that soil fertility map with the STCR recommendation and to arrive at nutrient recommendation. And these are some other in Kiran also, it was included in Northeast Kiran, this online system. And we also could develop the bilingual Marathi and English bilingual app, where these maps were taken as background wherever you cannot do analysis on the recent time, and that can be used to give fertilizer recommendation. So as Dr. Srivastava was telling, in a GIS-based environment, if you put all the things together and you layer it in a particular fashion, or say on the available knowledge, then we can arrive at particular recommendation for a particular soil. So ultimate our aim is to geotag each and every parcel of land, and then through a cloud-based system on a mobile telephony to each parcel of land through GIS-based soil fertility map, the recommendation should be given to farmers, and that should be handed over. Thank you very much for giving me this opportunity, and thanks to organizer, and thank you one and all. Stay safe, healthy and blessed. Thank you.
Thank you very much, sir. Thank you very much for a very excellent presentation for this, starting from the stratified random sampling to covering up several of those statistical measures used in this process, and also talking about, in short, about the various geoportals. I say geoportal has they're given a platform for posting all those spatial maps developed for soil. You also talked about the soil thickness. So these are very interesting areas which would further need maybe larger time for discussion. But we will pick up some of the questions from the chat box. One interesting question, one from one of the speakers, Dr. Amarnath Simple, that so where can we access soil moisture data to integrate in the abiotic stress management?
Soil moisture, okay. Soil moisture. Our institute is doing some, but we have very less soil moisture data for different soil. But on model, for modeling purpose, one of our team is doing soil moisture in particularly NICRA project. I know that they are doing. We specifically naming Dr. Manoranjan Mahanti and Nishan Sinha. They are doing some soil moisture data is available with them. So, but mainly our data relate to soil fertility in ISS. Soil moisture data, we have limited data, and we have also limited data on this environmental data. So you can access by writing to our director to reaching to the particular person, whatever data is available. But we have limited data on soil moisture, no doubt, because we have more data, of course, on soil fertility.
So the next, in fact, tricky question, I should say, from Dr. DVK Nageshwara, how best soil health card data can be put into use to generate scheme maps, probably at higher resolution?
Actually, soil health, that soil health data, total data, now as on today, that one small project from the soil health card scheme that was given. So what was decided, I was there in that committee. So that was given to Hyderabad, that remote sensing center. So they are doing, now they have come out with some maps. You can see that in the soil health card scheme portal, www.soilhealth.nic.gov.in. So that particular website, if you go for soil maps, so now they have uploaded some maps. Of course, there are some issues related to outliers, removal of outliers. We have given some boundary condition. Now they are removing that, but still that is available as on today. And some papers also came out from their data even. There was some discrepancy on potassium data. We came out with one paper actually, and then we suggested them to set some upper boundary and lower boundary for each this analysis that they are doing. But still, it is available. You can look for those maps in the, and also raw data is also available in Excel sheet. That is also available in soil health card scheme. So you can put your own this one. If you are soil scientist, you can put your own boundary condition that in this particular place, it cannot be less than this nitrogen and more than this nitrogen value. So from there, you can segregate data and use that data also. But of course, there are some issues with quality analysis. But this particular project, what I presented, mapping 175 districts, the dedicated sampling was done by the universities only. No other person did that, and it was done actually, and 1% sample actually cross-checked. So from there, but that is a kind of a bit older map. It is 1516. So you can access the soil health card data and map now on the soil health card portal.
Thank you, sir. There are many still questions to the soil sampling aspects and customer fertilizers. Maybe we should be taking this at the end probably in some meantime. Thank you very much, sir, for your very lucid presentation and holistic presentation, I should say. And we are privileged to have you on the on this webinar.
So, thank you. Thanks to director and all organizers for giving me this opportunity. And I am on the chat. I am uploading that particular GIZ newsletter. If one wants to see, they have published that as an interview. So if one wants to see what is directed sampling, how it was done in Balaghat in GIZ project, you can look for it. Thank you.
Thank you, sir. May I request the next speaker, Dr. Paresh Research. Can you hear me, Dr. Paresh?
Yes, Bhaskar, please.
Thank you, Dr. Paresh, to be with us. You can, in meantime, I introduce to you. You can share your screen as well. It's a pleasure for me to introduce Dr. Paresh Research, who is currently working as an associate scientist with CAF, that is Climate Change, Agriculture and Food Security, Wallach Institute of South Asia Summit. So his major research areas adaptation, propagation, crop growth modeling, climate risk management, crop insurance, and spatial analysis. He has contributed in developing several tools and methodologies, which include improved trigger design methodology for weather index insurance, climate smart agricultural prioritization toolkit, and crop loss assessment monitor. So he would be talking today on this topic also. Dr. Shirsat was also a postdoctoral fellow with CAF with International Water Management Institute IMWI. He has also held positions of spatial modeling specialist with IMWI and also was a research scientist with ISRO for quite some time. And he has worked in area, during this tenure on River Basin Atlas of India, development of spatial database and WebGIS framework for Water Resources Project, Survey Information System of India. Dr. Shirsat has more than 20 international and national research publications to his credit. I'm in fact privileged to invite again Dr. Shirsat to this webinar to deliver his presentation on the topic crop loss assessment in abiotic stress events, methodological challenges and technological opportunities. Over to you, Dr. Paresh.
Thanks, Bhaskar.
Thanks.
Good afternoon to everyone. Yeah, I think yes, it's afternoon now, and I'm really thankful to Dr. Pathak and Dr. Gaikwad and a whole team of ICR for inviting me to present our research here. I am Paresh. I work for CGIAR research program on climate change, agriculture, and food security. This program is a kind of collaboration across all the CG centers, and about like almost all 15 centers are participating in this CGIAR research program. This is on for last 10 years, and it's being implemented in more than 70 countries across the globe. So I work for CCAF's South Asia region, where we work in India, Nepal, Bangladesh, Bhutan, and briefly in Sri Lanka as well. So, this program, today's lecture, I am talking on like crop loss assessment with abiotic stress event, which is caused by abiotic stress event, and what are the methodological challenges and opportunities. I will be briefly talking about different stresses, but I will not be highlighting more on flood because my colleague Giriraj already covered that. So moving forward, Okay, so if we see the map where it was again thanks to Giriraj, he mapped several abiotic stresses in South Asia using different data sets, remote sensing, and many spatial analysis. So we found that several stress events are actually present in different parts of the country. And in fact, the South Asian countries are in one of the highly vulnerable to the climate risk. And with the advent of the climate change related impacts, we see that many meteorological and climate related disasters actually increasing day by day. Global analysis also suggests that drought and extreme heat events actually can affect global national production at 9 to 10%. And no wonder that India is actually again kind of in a receiving end, where largest of financial hits we are receiving. And we have even seen that drought, flood, and many meteorological disasters, in fact, can occur in the same location and in the same season. So that's the kind of widespread nature of these kind of the abiotic stress events are actually happening. So when going towards a loss assessment during these abiotic stress events, there are several tools which are already available. Several empirical relationships were already developed, and crop growth modeling is there. Several crop growth modeling tools like DSAT, ORISA, or SARAH, and in fact, InfoCrop. And thanks to Dr. Pathak, he is one of the lead developer of the InfoCrop. But what happening is we have seen many such impressive graphs which are which shows how our model perform in simulating different phenological properties as well as the grain yields. But when we try to go to use these kind of tools for the actual loss assessment, we face challenge. And that's what actually, what kind of methodological challenges we face and what kind of technological solutions we can bring, that I will be briefly talking on. So again, the process-based models, which are actually shown like kind of infocrop or DSAT type of models, they need a huge data sets. And those data sets are normally actually not available beyond the research setups. So, so what we can always have the different methodologies to create those data sets, but let's understand where this demand for loss assessment is coming. Besides our contingency planning and in general climate risk management efforts, we have seen that recent demand for crop loss assessment has been created by the insurance sector. And since we have seen insurance in India has moved from district to tehsil and now at a village scale. So that's actually created a huge demand, and that demand has actually led to development of several new tools and technologies. And also there are some other stakeholders like commodity traders, seed industry, and even there were value chain actors. They need information at different levels. Like let's say ITC needs, well, ITC Limited needs what kind of, what will be the wheat Sharbati varieties wheat yield before the harvest, so that their procurement can be channelized. So these kind of decisions they need, and they also need what kind of losses are occurring and what events are actually causing these kind of losses. So as talking about the insurance, the Prime Minister Fasal Bima Yojana, which we are having, which is third largest in the world, and about this year about 33 million people, farmers actually registered. It was more in a couple of years back, about 55, we reached to 55 million farmers. And there are different types of perils covered in these kind of schemes, like if there is a prevented sowing because of insufficient rainfall, or there is a sowing failure because of a prolonged dry spell or a flash drought coming just after the germination. And also there are provisions of mid-season adversity and the final loss assessment at the end of harvest, and in fact even post-harvest. So how they are doing the loss assessment? If we see the loss assessment in Prime Minister Fasal Bima Yojana is currently done by the crop cutting experiments, and the guideline says we need to do 4 crop cut at a village scale for a main crop. And so that's why we end up doing millions of crop cut experiments, that to a very narrow time frame of harvesting, just say 1 month. So the virtual MRV, that quality and monitoring, reporting, verification aspects of whole crop cutting is actually kind of a big problem to that system. And also we see, even if we do that kind of huge assessment, we have done several experiments and found that there is huge amount of intra-village, intra-insurance unit yield variabilities. And that also then leads to the questioning of those kind of crop cut experiments. So what we need is we need modern technologies and new tools for those kind of loss assessment. So, what actually kind of challenges we have? So we were doing loss assessment earlier at a district scale and then migrated to village scale. But we don't have the data set at that scale. So data at scale is the biggest challenge. So we can't simulate at a village scale using 250,000 scale data. We need to have better data. Otherwise, we need to have innovative ways to input crowdsourced information and maybe satellite information. So still, ground station weather data sets availability at near time is a challenge, though there are several opportunities in terms of satellite weather, it's coming up, but ground weather data is always more useful than the many times the satellite type of graded data sets. So again, a methodological challenge in initial stage of the crop development. Those relationships are largely based on empirical empirical relationship, and those are done in a limited agroecology. Like many these kind of experiments are done by ICR centers, even ICRISAT. And so to scale those kind of equations or those kind of empirical relationship at a scale needs kind of cross verification. And there are several tools actually which are available, like crop simulation models, but we cannot achieve the resolution which we want with crop simulation models and some of the tools, because what we need a pixel level or village level is a very high resolution. And the challenge again is this is a multidisciplinary effort. It needs expertise from several sectors, like expertise from agronomy, expertise from simulation, expertise from computer sciences. And then once we have those, that efforts then need to be translated into crop loss assessment. And many times several parameters are not available at scale, and we then have several assumptions like a pedotransfer functions, and then which can introduce varying degrees of kind of errors in our assessment. So considering these, what we did is we tried to come up with a multi-model and multi-stage decision support system. It's a part of CGI research program. So those multi-model decision system, it uses several kind of data sets, right, from weather, from the satellite data sets, crowdsourced data through the different apps, soil databases, and historical crop yields. Then there are multiple models, basically simple weather derivative-based models where we analyze weather and crop relationships, satellite vegetation indices-based models, statistical models, crop models. And then what we do is a hybrid kind of scalable model approach where we combine all of these to have a hybrid model. And again, as this application was developed for insurance purpose, the loss assessment was actually kind of designed to have prevented sowing or sowing failure conditions, mid-season loss. Mid-season loss meaning that if you have at the in the mid of the season more than 50% losses, then the insurance scheme had the provision of contingency payments. And then again, total loss at the maturity. Post-harvest, still we have not incorporated. It's kind of challenging to have to locate where it is harvested and still keeping still idle. It's lying in the field. So this is the kind of tool which we develop, and this tool is readily available on the web platform. Maybe by end of next month, this will be accessible to everyone. And the good thing is this uses most of the open source data sets develop in R language, and totally all the details and all the aspects of it are actually available. You may see the data sets like rainfall, temperature, radiation, soil, and most of them are open source data sets. So what it has is a different kind of modules. Like these modules are, if you see, based on satellite-based modules, then kind of crop simulation model-based modules, remote sensing-based modules. And these modules then are integrated in this tool for crop loss assessment purpose. So since it is actually, we are talking about different kind of abiotic stresses. It's not just one. We can see the precipitation anomaly, then there is a dry spell, length of dry spell. You can talk about drought, also about the maximum or a kind of unseasonal rainfall or a kind of extreme rainfalls. So these kind of abiotic stresses are actually considered while doing the loss assessment. And there are several methodologies which are being used to assess these kind of losses during the season. So besides the meteorological variables, there are also satellite-derived vegetation indices, NDVI, GCVI, those are also available. And the derivatives of these indices are also available. And when we have a comparison of, let's say, when you have a loss assessment, it's just not based on one method. So the thing is that at different stages, you have different type of losses, like let's say prevented sowing, small pockets, maybe sowing failure. And then the most important, if you see the loss assessment at a kind of harvest stage, there you may say that this loss assessment is different categories and different level of confidence in assessment. And this confidence in assessment is coming from different methods. It's basically an agreement of different methods showing the same loss. So, and at the same time, user can actually correlate this condition with the maps which are actually available in the terms of meteorological derivatives, or maybe in the terms of vegetation indices. So this is a tool which is readily available for everyone, and this operates at as of now at a state level. You can't operate at an India level considering huge computational resources required for this. So again, I explained earlier that achieving at a pixel level is a challenge. So, but remote sensing provides actually a very important elements to achieve a pixel level loss assessment. So if you see here a graph which I am showing, what we are trying to do is trying to assimilate the remote sensing data sets in the crop models. So in that sense, suppose the blue line is a crop simulation model LAI, which is simulated by crop simulation model. And we are somehow in the, let's say 40 days. And what we see the green line here is the remote sensing based leaf area index. And there is, that means crop simulation model is off the track and it's not simulating correctly as per the field condition. So we can introduce the correction factors. Like there are several methods of introducing the correction factors, reinitialization or maybe Ensemble-Kalman filtering approach. So we can introduce and bring back this crop simulation model in this trajectory. So that our loss assessment actually becomes more and more accurate. So what we did in one of the experiments in Aurangabad district in Maharashtra, we use DSAT maize model and used kind of a soil moisture and LAI simulation in DSAT maize model. So there were several simulations which we did. I will briefly just tell, like open loop simulation was there, then assimilating soil moisture plus LAI, and then only LAI simulation. So what we found that we improved from the open loop to soil moisture and soil moisture LAI. We certainly have the improvement, but that improvement is still a challenge. What we had a better characterization at a pixel level, but again, availability of data at scale was an issue because this was done using I think 500 meter LAI, and which itself is very coarse considering the smallholder farming systems which we are having. So that's one of the important story, that we need to have data at scale. So coming towards the next part, this is like if we see, we have worked besides there was a CAM tool which I presented, but there are several works which CGIR CCAPS is doing on crop loss assessment. You heard from Giriraj, he is working on index-based flood insurance, and where he is actually trying to kind of flood stagnation and flood depth with the crop loss, correlate these two things, and the whole insurance product is being developed around this. And these products are actually being accepted by Bangladesh governments, and also the trials are actually being done in Bihar, and I think they have the plan to release it in Nepal and Sri Lanka as well. So next is a very innovative approach where International Food Policy Research Institute, again a CCAPS work, they are using smartphone-based photographs for kind of loss assessment. And these photographs, it's not like a general photograph. They have the protocols of taking a photograph so that we photograph same view during the plant growth, maybe once or twice in a week. And then those photographs are actually developed and correlated with the crop loss libraries, which were actually developed earlier in the project. And then there is one more tool, which is on crop yield forecasting. It is CCAP's regional crop yield forecasting toolbox. This kind of tool was developed almost 7-8 years back, and it actually has several dimensions which can be used for our work. It's like it has crop simulation models. You can run crop simulation model in a special platform. GIS, it's like it executes it in a special platform. It has a climate prediction tool. So it's not like that you just do the simulation at the end of season. You can have the climate prediction angle, and you can also provide extended range forecast to this tool and get a kind of assessment that what will be the effect on our crop loss or crop yields if we have the different type of climate scenarios. So far it is having DSAT, AppSim, SARA-H is already there, InfoCrop is being plugged in, and very soon it will be there. So these kind of tools actually see if we have these kind of tools, and we can answer different answers. We can like give the different answers. Like a farmer wants to minimize his risk considering the tercile probability of climate forecast. Let's say he is having, it's predicted that 60% chances that there is a below normal rainfall this year. So can we advise him? Can he make a decision based on that, what type of crop to sow and what type of insurance product he should buy? So I think these kind of tools actually will help in judging these kind of, will help in making our crop risk management, climate risk management strategies more solid. So what kind of technological solutions we see? So I earlier told that there are actually, we use in CAM tool several satellite-based precipitation estimates. But unfortunately, for a country like India, only 140 stations are being reported in the CHIRPS platform. And so that's actually, it's a satellite-based precipitation, but without any ground station data. But same time, several state governments like Maharashtra itself, I know that they are pushing daily crowdsourced rainfall data for more than 1,860 revenue circles. So why can't we merge these two and create a better meteorological parameters or maybe rainfall estimates, so that our loss assessment and impact crop health status information system becomes more and more robust. Also, we can assimilate remote sensing data sets so that we have near time. And it's not just we can assimilate LAI, you can assimilate soil moisture and many other products like evapotranspiration and many other. And nowadays, what is happening is developing a kind of a scalable yield mappers, like combine all these things and have the best of every approach, so that we have the more and more accuracy, and same time it is not a kind of a data hungry system. Then it's not possible that we will get data at scale. It's not possible, and it's not economical also to get all the data sets at a scale. We can think of using innovative technologies like remote sensing to derive some of the crop management practices or some of the data sets which are required for our loss assessment models. And if you see nowadays, a lot of buzz is around big data technologies, and we can use those. We have already millions of field observations. If you see Prime Minister Fasal Bima Yojana, it is collecting more than million of crop cut experiments. Why can't we use those? Then there are most of all our research institute having huge data sets on weather, then photographs, and this can be clubbed together. In fact, we can have the data sets of market arrivals and in fact news mining. Like there are several disasters which are being not recorded, or they don't have data sets, official data sets like cloudbursts, hailstorms, or maybe flash floods. So can we use news mining kind of things and build the bigger data sets for actually making our models more accurate and robust? So this is okay. In summary, I just want to say that data at scale is a challenge, but this does not stops us from using our existing models and tools for the crop loss assessment. In fact, actually we get a more innovative systems in place if we use remote sensing based or new tools like big data technologies can be actually plugged together to have the accurate loss assessment. That's all from my side.
Thank you, Dr. Paresh, for a very nice presentation covering many aspects, particularly the methodological challenges and the technological opportunities. It is indeed known to everyone the data set availability limitations are in fact a crucial point which has been defining the success of several of such programs. We have got certain questions in chat box. One is, we'll quickly take them. From Aruna Mohan, how best these assessments are in correlation with the ground data? I guess in remote sensing data assimilation, this has been addressed, but I would like to know more from Dr. Paresh if he would like to add on this further.
See, so for ground data sets, we always calibrate our systems with known data sets. So So there are some challenges in terms of initial assessment, like prevented sowing and sowing failure, where we don't have the ground data sets at a plot level, but we always correlate them at like a different government, state governments actually have the data sets like a sowing reports. So we correlate that, and they come. It's not like we can't expect accuracy of like very high accuracy, but they are moderately accurate.
Yeah, thank you. There's still four questions pouring in. Probably since we are running almost half an hour late, we'll be taking at the end in some time. Thank you very much, Dr. Paresh, for gracing this occasion, this webinar with your presentation. And we'll write back to you for some collaborative opportunities we see from your presentation, wherein NISM also can contribute to certain areas. Thank you very much, Dr. Paresh, once again.
Thank you, Bhaskar. Thank you, Dr. Patel.
Thank you. We have still two presentations left. Next in our row is Dr. K.P. Suresh, sir. So, so you can share your screen.
Yes, yes.
Yes, sir, you are audible, very much audible.
Okay,
yes.
okay.
So now this abiotic stresses have caused the biotic stresses to manifest itself, causing a widespread effect, which calls for disease modeling and forecasting also. Pardon, sir?
Sir, is it now?
Yes, it's visible. Your
no.
screen is visible and you're also audible.
Okay, sir. Okay. Shall I continue, sir? Start.
I will just introduce it couple in 30 seconds. So, Dr. K.P. Suresh sir is a principal scientist working with National Institute of Veterinary Epidemiology and Disease Informatics. He has done his PhD in biostatistics and his area of specialization is epidemiology, disease modeling, meta-analysis, remote sensing, and GIS information systems, and biostatistics. He has to credit 70 research papers, and he's also he has got several recognitions to his credit. And he has developed mobile app for livestock disease forewarning, which was released by Union Minister of Agriculture in December 2017 at Krishi Bhavan. With this brief introduction, I request Dr. K.P. Suresh sir to please deliver his presentation on the topic. Over to you, sir.
Yes, thank you very much, sir. Thank you for Dr. Pathak sir, Gaikwad. I'm very thankful to you for providing me this kind of opportunity to display my capability to the audience. Here I'm just going through how you have developed the forewarning system with using the artificial intelligence system, gathering data from the remote sensing, different meteorological data and livestock data and disease data, and how it is going to work and how you are disseminating. I'm going to deal with that and explain how we are doing it. Thank you very much. And my topic is implementation of artificial intelligence to for geospatial data analysis with special reference to livestock disease forecasting. This artificial intelligence, you know, that is a very buzzword now, and it is everybody thinks it's already there. It was there since many years, but you are not using it. Since the availability of the computing systems, advanced computing systems, this artificial intelligence system models or artificial intelligence has become more popular and familiar nowadays. And it is now systems are available, computing systems are available. That is the reason we are now thinking of artificial intelligence. Otherwise, we have to stick go with traditional methods like small regression models and other things. You see that the artificial intelligence, how it works with the machine learning models, and how what are the mechanism, how it works, generally methodological aspects, little bit on methodological aspects also I will provide you. So it's got a 1 minute. Sorry for interruption. Some hanging server. 1 minute. Server issue. Slide is not moving. Sorry. Share again. Yes.
PPT close again.
Sorry, sir. 1 minute.
Zoom. Share. Close my method. Share.
So your presentation slide is
Sir,
ready. You can,
sir, it
yeah.
was distressful. Sorry for that.
So you can go ahead, sir.
Sir. This is the artificial intelligence. It's a overall as a tool. It's a tool. Artificial intelligence, not a models. Under that, machine learning will be there. Deep learning will be there. They all many people know that or very well how it works nowadays. This is very important, particular agriculture activities, particularly. It's very important, and implementation becomes very tough because we need a manpower, resources like money and manpower. And in this capacity also in India, I don't think we have capacity, but we need to implement it. So, you know, the machine learning program, how all this works and all. This is how type, these are the type of machine learning. One is supervised learning, unsupervised learning, and reinforced learning, where supervised learning, you know that we are all doing, there are groups already exist. There are 2 groups, 3 groups available already. For example, treatment and control. How best we can, new treatment comes, new person comes, how to assign the group, particular group. There are 3 persons are school, for example, children. We have made a 3 groups identified. So new children comes, where exactly you will fit into that. That's a supervised learning. Unsupervised learning, where there is no group available. We don't know what are the groups available in the data. So, or in the population, we need to make a first group. Then we start thinking of are predicting the new person comes, new treatment comes, where actually matches. Reinforced learning is somewhat this one, and it's a little bit complicated. Like it is a like a switcher. A lot of switches are there, lights are there. We need to train ourselves. That's the way it works. Reinforcing, that is a little bit more, but more complicated, and we'll focus on supervised learning. And in our concept, I will more focus on supervised learning, where groups are made, 2 groups are made, case control, and I try to allocate, identify the factors responsible for the occurrence of the disease or groups identification of a particular space. Deep learning is a very important nowadays. Many people are working on that. Under that, we know that neural networks, convolutional neural network is image processing, recurrent neural network. You know that recurrent neural network in nowadays Gmail process, when you are handling Gmail, when you are replying back, some answer will come. That's all related to the recurrent RNN, recurrent neural networks. It's all depends on how layers are, hidden layers are linked to each other. That requires a huge computational process. You know, data gathering from the different like this through using a layers, it's very tough, and it requires high capability systems. CNN generally it's a classification of the images. That's works very well. Actually, we are also trained. We are also tried in our lab to develop identification of develop a program for using CNN algorithms. But you are using R programming. Of course, you know the computational challenges are in the neural application of neural networks is very. So these are the application of artificial intelligence, image processing, character recognition, and all. We are aware of that. That's I need not too much go into this deep into that. So particularly artificial intelligence, I was thinking that, for example, we can use an artificial intelligence system where we develop a database. For example, farmers requires they want to sell their produce. The vendors database will have farmers database will have. You see, before harvesting, for example, if you develop an application where vendors database is there, bidding will happen in the online. Farmers will tell before harvesting 2 days or 3 days, he will bid, he will open it. Then vendors will start bidding it. So you can accept after 2 days. Harvesting, post-harvesting losses can be controlled, and farmers' income also can be increased. Such kind of systems should be developed. Applications should be developed. So we have seen Ola cab applications. Business is happening, whereas farmers no application is happening. So we need to develop some application for farmers, which will help for the farmers to increase their income. That is the idea of artificial intelligence can be utilized for that purpose. There's already drug discovery at all, it's applicable. Right? Then I do what is happening. One minute, sir. The system getting hanged because animations. Sorry, sir. 1 second that I will adjust it. More animation support.
Share the stop noise. Okay. Stop share.
Again, let's see.
Instead of slideshow, but I'm like
Huh? Any process. So these are the problems. Sorry, sir. This machine getting our system getting busy. What is
So it's visible. I request Dr. Suresh to catch up with the timing.
Sorry, there was a disturbance because our people have put a lot of animations in that. That's a maybe reason. Sir, we are also working out on abiotic stress, how people are working. I was going through that wonderfully done. People have done wonderfully. And in that also we can, how we can predict. Prediction is very, very important for whether it is a deficiency, stress, or whatever the type of stress or diseases, whatever it is, we can use a artificial intelligence system and predict the diseases. So these are the abiotic many people have done and wonderfully done. I appreciate that people have done a lot of work on that. So here it is a work which we are doing national NADRS, which is National Animal Disease Referral Expert System. What it does here, see this is system we can refer our website and Nivedi, where we have developed a system where actually everything incorporated, which predicts the data disease 2 months in advance. Any 13 livestock diseases we are incorporated. Diseases are collected from the different states, disease outbreaks, and accordingly we have livestock population data annotated. District level, we are all 700 districts we are predicting now. 2 months advance we are predicting the disease so that the state governments, Department of Animal Husbandry can take preventive measures before the disease can occur. This is what the basic aim of the NADRS. So we have to provide the solutions to the farm departments so that they can take preventive measures so that disease will not occur. That's the idea of that. And for that, we have developed a lot of methodological concepts so that disease we predict, what we predict should be accurate, as much as possible accurate, provided data is good. So this is the basic idea of that. We are also developing a risk map, which is otherwise called vulnerable maps. In this, we have given all the how we alert the different methods, communicate we develop a risk for the disease occurrence, and we'll develop and communicate. Risk communication is also we are developing some methodology how we can communicate to the different modes to the people, farmers, veterinary departments, and all. This is how the, for example, prediction happens. Suppose we select anthrax disease. There are 13 diseases we are predicting now, and Karnataka state is select. The disease will be all what are the districts available, and districts with the risk map also will predict risk map also shown, and the preventive measures also accordingly is given. This is how the it is done. With this, what happens? The methodology is how data is capturing by remote sensing data, and disease data is available last 20 years data, outbreak that is available district level. Now you are getting village level data, and you are taking remote sensing and meteorological data, livestock population, as this one. Different servers were meteorological data we are taking from GLDAS for many around 15 parameters we are gathering. And remote sensing data we are using only NDVA and using the MODIS product. All the products are using. We need a little bit error will be there, but still we are using the products. And livestock population from these livestock sensors of 19 we are using it. And data, see here it is what is happening. Data cleaning is a national level data. We have to gather. We have to produce every first you will start before 5th. We have to start predicting. So we need a what is the important is here. So much big large scale predicting all the districts, 700 districts, gathering data, and it's very time consuming. We have to do it in 2 to 3 days prediction. That's how we have applied the artificial intelligence system. It's gathering the data from different sources, cleaning it, annotate it, model it, and send the results to the people. This is what it happens in 2 to 3 days, and results will be forecasting data, and all these things happens in 2 to 3. That's how we have built our code in such a way that everything, it's a we produce around 100-page prediction reports within the 2 days. That's all system that the system automatically does. This is how we have done using the machine learning program. Different machine learning programs are adopted. In that, all the models may not be giving the results. So what we'll do, once all the models are updated, they will give the results. So here, before applying the results, what you have a case data, you have a control, corresponding control data you will generate. That's called pseudo controls. Pseudo controls are very, very important. If you we are failing in the selecting the pseudo controls. Case data available, but pseudo controls is very problematic because many times diseases are not reported. So that's the reason we are not, maybe the quality of data depends on the control rather than the cases. So I will explain you later on. Stop sharing. Huh? Huh? Sorry, sir. Again, you get angered. This so many maps he has built. See,
Just 10 minutes. ಇದನ್ನೇ ಕೊಟ್ಬಿಡಿ ಸರ್.
ಅದು ಕೊಡಲ್ಲ ಬಿಡ, ಹೋಗುತ್ತೆ ಅದು, ಏನು ಪ್ರಾಬ್ಲಮ್. ಎಲ್ಲಿ ಬಂದಿದ್ದೆ? Sorry, sir. Little problem in the where is it? Share some issues are there. So what you have to do is using machine learning program, we collect the cases, we create a control data, pseudo controls. We'll try to mix it. Both control and cases will be mixed. Then we use a models. These are machine learning models to classify the case and controls. Which model gives the better results, that will be taken as a for prediction purpose. We have approached. We have developed a seven approach system. How we can see the endemicity, spatial endemicity, temporal endemicity, GA values, JDC index. That is autocorrelation system, something clustering, detection of clustering, cluster modeling, CAT scan. Then we will develop a risk map where we can predict here. We can use a risk map where using the models, we can get a risk map like this. The risk assessment. In this, you can see here, once the risk models are developed by different models, around 20 machine learning program will adopt, all the 20 will give 20 output. So all the 20 output, which one is better, we don't know. That's why we are using assessment evaluation model like Kappa, ROC, TSS together. We take TSS together, which gives the best average score. Average, we collect average score. That will be the risk. We are developing a risk. Best, for example, blue tongue in Karnataka. With R0, we know that nowadays because of COVID, everybody knows R0, basic reproductive number. That also we calculate and superimpose on the R0. Wherever risk is there, we can assess. Even good risk is there, but may not be R0. Secondary infection may not be there. So wherever the risk is there, secondary infection is there, accordingly intervention can be modified or developed. This is the risk map with R0 we are imposing, and this can be used for the developing. We also developed blue tongue in El Nino effect, La Nina effect, and all other things. We have developed a simulation model like this, how NDV and BT incidents, blue tongue incidents are correlating with LST and all. This is one simulation we have done, climate change, how it is happening in Karnataka. There is these are the El Nino effect and La Nina effect. We have seen the disease incident. Definitely, impact is there in climate. We wanted to measure. We made it. So this is another one we have done, development of GS-enabled early warning system for heaven influenza, but still in the development stage. What we have done is cases we have collected over the last 15 years, I think. And accordingly, pseudo controls are generated, pseudo controls in this. And this case and control are mixed, then used models and we got this was HY known, the risk map. It's called vulnerable map, what you call. So this map, which we can use it for prediction of future prediction also we can use it. This is how the risk map is developed in the disease forecasting. This is how. This is main important is that we have to understand that there is uncertainties. Despite climate changes, disease model, power of climate and disease model, considerable uncertainty remains. Identifying these uncertainties, very important is when you are modeling, there will be uncertainties that we have to identify. That is the basic idea. And highlighting the importance of quality of data. Data is a frequent machine learning program, general machine learning models, we need a data, good quality data. And to improve the model accuracy, confidence together is translating the uncertainty into the model inputs, into the uncertainty in model outputs are important benefits of the model. Modeling, we need to try and go on doing, then automatically it gets accuracy over the time. This is how we are communicating using this. We are having reports, monthly reports you have to publish. It's 100-page reports, which will be generated almost 2 days. Within 2 days, we have to submit maximum 10 every month. 10th of every month, you have to submit a report to the state government. Therefore, we have developed a artificial intelligence system, which does everything from capturing data, annotating, cleaning, annotating, modeling, almost forecasting everything. The system, address V2 website itself, almost automated. So we can see this is how the forecasting goes, auto messaging goes. Automatically people will get messaging, and for bulletins will go in the web application also there. Simultaneously, we have developed mobile apps. So many mobile apps we have developed through mobile apps. We are communicating the risk. Sorry, it's hanging. Some issues are there in the animation.
So you can continue.
Sir, only 1 second. We'll just add it. Stop, sir. Again, you have animation, some problem created. So here we close it. But both. No. Sorry, sir. 1 second. I will just rectify it. Some animation problem creating problem. Animation problem. Share it. There is some issues with animation, I think. Sorry for the interruption. See, many questions are coming after prediction. You are sending results. Already people are using it. So questions are coming for us. What is the accuracy? What is the validity of your results you are predicting? Many people are questioning. So we cannot disease prediction. Once you do the disease prediction, we cannot test it, validate or validation or whatever you cannot do lab. We need to go to the field and validate it. So what you are getting? You are getting a newspaper clips. Where once you predict within 2 months, we get a newspaper clips here and there, whatever, wherever the outbreak occurred, we collect it and see whether we have predicted or not. Accordingly, we validate. And also additionally, after 2 months, we get a reports. How many predicted, how many reported. These are the things we are predicting. These many. False positive is not a problem. False negative should not happen. Our prediction should not be false negative. Therefore, accordingly, we are validating by the news clips and other methods. These are the validation reports. Almost all out of 10 prediction, we are getting 6 to 7 good accuracy. We are predicted most of the times. That's how we are predicting. Thank you very much, sir, for providing the opportunity for sparing my knowledge.
Thank you very much, sir.
Sorry for the disturbance, some issues happened. Anyway.
It is indeed an excellent presentation, and we were privileged to listen to you. And in fact, looking from end-to-end automation of a real-life problem being handled for disease prediction, and that too in 2 months in advance. It's a case study, we should say, that can be referred for end-to-end implementation across crops as well, depending on what methodologies suits the process. And thank you, sir, for covering some of those comparative matrices on ROC, TOC, and also trying to tell about gathering data, some of the issues related. And we appreciate your presentation, sir. There are certain questions, but we would, due to paucity of time, we would be switching over to the next speaker. And as time permits, we'll be taking up the questions. So thank you very much, sir, for your next presentation. Dr. Chandrasekhar Biradar, sir. Yes, sir. Thank you very much, sir, for joining us in your very busy schedule. And we apologize that we are running a little late from our schedule. So you can share your screen, sir. Till then, I will introduce you very briefly.
Sure.
So we have with us Dr. Chandrasekhar Biradar. He's a principal ecosystem scientist and leads ICARDA's Geospatial Science Technology and Application Research activities. Dr. Biradar has led production of world's first satellite sensors serving irrigated and rain-fed croplands, and has also developed a number of remote sensing-based methods, algorithms, and tools related to land use and land cover mapping, biodiversity assessment, water productivity, eco-epidemiology. And his current research work involves developing geospatial mechanisms that deliver interventions for smallholder farmers. More precisely, he has authored more than 200 publications and has several honors to his credit. Means it's a very big list, but I should mention that he is a PhD in remote sensing and environmental sciences from University of Pune, and also is a postdoctoral fellowship he got to study at University of New Hampshire. With this very brief introduction of our today's very knowledgeable guest, I request Dr. Chandrasekhar Biradar, sir, to deliver his holistic presentation on the digital augmentation. Over to you, sir.
Thank you, Dr. Bhaskar, and the convener, co-convener, and director, and all my previous speaker. They made fantastic presentations that made my job easy, and all the audiences for the patients for the bit delayed the sessions. I understand this is so many the interesting topics, and it's in fact like being in the technology, I'm glad to see so much of things is happening in all the fantastic work presented by my previous presenter. And this is basically made the pathway very clear. And they explain all the terms and jargons and how we use the technology. So just what I move towards exactly the holistic management. And before that, I just give the background of what ICARDA and what the CGI are. And the CGI is the Concept of Interest in Agricultural Research and working across the world. And ICADA is one of the 15 Central Lake Summit and the IMI they presented in the past, previously. And we basically work on the dry areas of the developing world that you can see in the both tropical and tropical dry areas, where ICADA is based here in Beirut and Cairo, but also there are 15 locations in the different part of the dry areas of the developing world. And basically it's a kind of a decentralized research for developmental the research, and mostly focus on combining component research with the system research. And with 5 strategic research teams that's basically focus on genetic resources, adaptation to climate change, building resilience, and promoting value chain policies and enhancing the water and land productivity. Plus 5 what you call a cross-cutting thematic areas, and that includes the big data, scaling, capacity development, and gender. So I just mostly focus on the big data because of these segmentations that the topic talk about. And as you know, that global challenge is facing, this is the stress is just one of the factor. And basically it's you moving away from our what you call a planetary boundary limits, and producing the somewhere good food, bad food, and eating the wrong way or unsustainable way. That basically bring us the challenges of the what we eat. And this is basically I bring back to the what is called what human health, so that what is required and how we consider the health. I think that's applied to the plants as well. And life is the continuum of the conditions in the process, how we grow and what is providing surrounding areas, and that understand the factor that connects to that continuum. And often we know that the biotic stresses and the abiotic stresses, they are kind of interlinked to each other. And this is where why we need to have the more on the biotic stresses, and does that need the holistic approaches? Let's go through the quick slides journey. And I just start with the health of the human beings. What in order we need to be healthy, we need to have a clean air, a water, and vital food, and the good space and surrounding environment. And that required a good mind and body. Basically required the inputs, what you go into the systems, and that's including the food and air, and state of mind, and the restfulness. And you just bring that into the same thing in the how the world food is productions in the domain that require basically diversified systems that link to the gut biome, and that link immunity and farm diversity. And just put into the same concept of what human beings we are living. And I put the 5 key components here, that is the soil and water, climate and diversity, and the seeds. And I put the more emphasis on the biotic, because of the biotic stress is so critical that leads to stresses. And let's look into what are those, someone can mute all of them, so sorry for that. And I just start with the soil. Soil is, I think, source of the resistance for the most of the stresses, and whether it's soil organic carbon, soil structure, and types, and nutrients, salinity, and most importantly, I consider the soil microbial fauna. So that's basically linked to the lot of the stress biology in the plant. Then it comes to the water. That's what my friend Giri covered quite a bit on that. I'm not going to talk much on that. Basically, this is under the important stress required into managing along with the soil. And then comes to the what the Paresh was covering on the climate change. And this is basically the prominent factor is the heat and radiation's impact. And also, of course, in the living in the cold country, like frost and the wind chills and the humidity, that's going to impact a lot of the stress conditions. And of course, we usually link this diversity and seeds to the biotic, but I would say that that's linked to the abiotic as well. How the crop rotations and crop choice we make it, companion, germplasm, farming systems, and abiotic stress assemblages, how the plant interact each other to overcome this, what we call abiotic stresses. And that basically link back to the farming system diversity, and whether it is the variety, source of the seeds, where it's coming, whether the input varieties are native heirlooms, or it's like a neglected the crop species, what called future food systems, or resistance involved in that. So that if you put all these 5 components and the subcomponents, all the 25 to 30 subcomponents together, this is what brings you really the holistic approach of the stress management. We cannot just look into only one factor and ignore other one, because of this is where the stress, as like human beings, if you have too much of the stress conditions, it tends to have a more diseases and disorders. And this is how we can manage and what are the data and tools we can use it. And already they covered by my colleagues in the quite a number of slides, very, very interesting, and the information is providing there. So basically, we look at the system, at the agroecosystems that is inclusively integrated. It can be any number of the components, but comes back to the food. And this is one of the important factor among the 5 stressors is the soil. If the healthy soils is basically healthy life of the both plants and animals, and that is where the real what's called a stress busters in terms of the both plants and animals, and in terms of the agriculture as a whole. So living soil is a basic source of the stress-free management because of if the soil is rich in terms of the mulch, organic matter, nutrition, and fungi, that is a mycelial impact on the soil, and the way that we do the crop rotations and diversity, farming systems, and water holding capacity. Basically, that's the good soil is the source of the resistance to the stresses, pests, diseases, disorders. I would say that this is where key emphasis is required. I give a lot of the examples, even on my own farming systems and our own experiments, including the different levels. And healthy soils, yeah, is the healthy crop. That's where the beginning of the what's called the better management. And this comes to the climate change. Often that is looks like a quite a daunting task to do at a very large scale domain. And of course, this is a large domain, the anthropology impacted natural process where the climate is changing. It's impacting on the balance, whether it's a 1 year is very good year or it's a surplus year where the floods and all those things happens. And the next year, immediately next year is a drought year, like a deficit year. And because we not have the good amount of the what you call organic matter in the soil organic carbon, and the humus in the soils, the most of the soils, whatever the excess water comes in the high rainfall area, high intensity, basically they drained out, so that we not have the on-farm water management is lacking to that one. So that's technology is there to identify where are those gaps and where are those hotspots of this kind of issues. And then you can look into those climate issues into the growing seasons. And we asked with the sadder growing seasons, and look into the overall the India precipitation this year or previous year and the long-term averages. There's not much change in the total amount of the rainfall received, but what is happening is it is the pattern, it is the locations, it is the onset and recessions. All that is really impacting that. So just looking at the example we did for 30, 40 years of this, the seasonal variabilities into that. And one area within the desert, there is a high rainfall, other is a low rainfall, but that's both leads to the loss of the water and the soil. And that's basically brought us back to the building a healthy food systems. That's really need a rebuilding the soils. This is what we build like the stress-free agriculture. And that is where we need to look at the number of aspects there because of the biodiversity of the seeds. This is just giving like I took this picture this morning, and I'm just putting this the one hybrid seeds in the left side and the native, the heirloom seeds in the right side is the gaur bean, the what we call cluster beans. That clearly indicates in the same pot during the same conditions how this the germplasm is going to impact on the stress and the heat, because of we have a couple of the heat waves a few weeks back, a bit hot, dry conditions. Is already this impact on the plant. So this kind of the little bit of the heat is impacting that much, but there is a way to deal with that when it comes to the number of those stress resistant varieties and the farming system dynamics. And this is basically what I call it the digital augmentation that required a data-driven decisions that builds the resilience systems. And we cannot just only focus on the ecologically sustainable options, but you need to look at the economically viable options. If you manage the system so holistically, that links to the food and nutrition, and that's basically and the health of the plants, soils, animals, and the people. So this required very holistic approaches, and that reduces the investment to go into the growing the food, and also the post the things, because as we talk a lot about the data these days and big data, and the public domain data is growing exponentially. That demands a new innovations and strategic approaches to untap its huge potentials in terms of whether using the AI, machine learning, and augmented technology, how best we can bring back here. Because here is already like we are here, but is most of the unstructured data, but that is where require a lot of investment to do that. And also we need to do that the fractal approaches, because of the stress management can be at an individual variety level, individual gene level, and is a crop level, at the system level, there's entire landscape level. This is where the what you call the big data, they provide very interesting the approaches do at the fractal dimensions, and that provide a very holistic case scale for the management, so that you can adopting the particular varieties, identify those things, and bring the right variety to look into the particular crop and management. And this is where we need to look at it very the augmented technology and digital augmentations and digitizations is very need of the essentials, because of we talk a lot about the what we call the model based and machine learning based and satellite data based and a very big holistic big way, but often we forget the local intelligence. So you need to leverage this technology and local intelligence that feed into the expert decisions and algorithms that able to provide a site specific in-season indicator and diseases, and that help us to what we call address the stress management of the crops. I'm not going to go detail in this one. What is basically the showing here is this is the beginning of the new era of the digital augmentations, big data analytics for the farming systems level. As you know that the amount of the gadgets and tablets and IoT is increasing drastically in the last few years, and see that almost like a lot of farmers and householders having this smartphone, and that feeding a lot of the data driven, and now we are moving towards the automation, what you call programmable era, so that we are kind of the transition between the tableting era, because we all are looking at the computers and screens, and then there is automation is triggering, and this is what required there's one of the huge data lack is the local intelligence, because often we treat that farmer as just we don't have the knowledge on that one, but the farmers, when I meet them, interact with them, they are the super intelligent than any scientist when it comes to the really managing the stresses, but they lack the what is called vision. So this is required a cognitive systems. We are making use of the local intelligence because of this, all the phone technology and cell phones and AIs, machine learning, earth observations, cloud computing. So that's really bring us the what you call conscious systems, where I'm not going to talk on that one here. So this basically drives back to the future, what we call a multi-layer farming or biodiversity farming, integrated farming. It's not new to the Indian systems or anywhere in the world. This basically is existing for a long time. So what we call that, bringing that, what's the digital augmentations and framework, we need to build that framework driven by the data and a local intelligence interface. That interface is the decision making that has work under different scales. So that basically I group into the 4 functional domains. The domains is a functional domains, basically they interconnected each other, how that integrations happens at a domain level, and modular, because when you look into the pest or disease or disorder, the soil or crop, so that you have to look into different aspects, because you cannot manage all together one, but you have to disaggregate and aggregate that, and that comes to the service domain. This is where the hands on the farmers or the decision maker, they can make this use, so that optimize the research interventions that help us to build a resilient cropping system, the resistant to the pest and disease and the stresses. That's basically the basis for the sustainable intensifications or ecologically the right crop at right place at right time. That builds us what we call a financial inclusions, because we reduce the number of the inputs going to the manage the stress, basically reducing that. That's where I see that is the top of the management in the stress. It's building a resilient systems. So this really demands for the data driven digital augmentations, that interface for the very big scales that starts from the sub-meter level to the hundreds of meters, and it's daily data available. We can make that decision. That's a dream to have this kind of the high resolution data on daily basis. In the just 5 years ago, that's huge changes happen in the few years. So as my colleagues in the past, in the previous the topics, they covered quite a bit on these conditions. A data source and the augmentations is really happening that, and analytics and decision required, that is understand the conditions, growing conditions, crops, crop types, rotation, soil, its characteristics, weather, agronomy, trade, market analytics. Basically, you have to bring what you call a meta-analytics. This is happening in our health systems in the big scale, because of now we are moving from the treating individual head, leg, body, but basically now looking at it the entire the whole body as a whole to treat a particular diseases and disorder. That we call a meta-analytics and meta-treatment. I think that is what we need to do. That one, the same thing when it comes to the stress management agriculture. So there is enough tools is available, analytics available, the cloud computing available, and nowadays, like instead of I'm worried about going here and they're collecting the data, I just go to the Google Earth Engine, the Google Cloud Systems, and Azure and AWS, and all the required data to the model is sitting in one place. If you look at the Google Earth Engine, Google what's called Weather Engine, and that integrated tons of the data sets available free to use within the system, so that you can, what is required is a smart way to build an algorithm that can connect all those open access databases and the citizen science database together, that can build into the such integrated system that provide an inclusive system. I just give you the few because of the time constraint. I'm not going to go detail of these, the algorithms, how it works, and how that can be trained to make a decisions to the holistic way of managing the agriculture. And here, basically, when the COVID hit, immediately within a day, we able to understand that where the crop stress is happening. And when locust comes, we able to track them that this is where the pathways is happening that. And within the large system that, okay, where are those agriculture is declining and what are the stress factors? For example, here I'm showing in corner of the Nile Delta here in Egypt. And the same analysis looking into about 20 years of the data, look into the daily data for the 20 years and come back to the what's happening the system level. If I was in the previous about 10 years ago before this Earth Engine and machine learning made it happen, it would have been taken like 6 months to do that one. And this one, you just did it 1 minute of looking, understanding that how things is happening. There's a smart way to handle these things, anything, so you can bring it to your ideas. And that is the algorithms there, data is there, and come back to the source systematic analytics and look into all those the declining vegetation in the domain in the 5 years, 10 years, or 15 years, or in the fluvials of every 2 years and 1 year. So much of the flexibility to understand why there is certain area of the agriculture is declining, undergoing the stress. Is that salinity, is that drought, is that flood, is that inundations, or is it just simple the mismanagement of the crops or the monocropping? Like that, you can able to do that. When you not to look into the everywhere, go to that particular data, look, but is all data sitting there in the open access databases. You can do that. So this I'll give the one example here, going further into the very small watershed scale or which in the command area scale, and how we can quantify that in the multi-layers at individual farm level and to the basin level, and to understand that integration of innovations is required and understand where are those the vulnerability areas there in the long term, within the 2 years, in the 5 years, within 10 years. For example, what are the frequent drought affecting areas in the given lake? Or where are those key vulnerable areas in the big scale? And where we can intensify the systems. We cannot do the intensify systems everywhere. I cannot go to 3 to 4 crops everywhere. We need to identify that is intensify system that is sustainably viable. And of course, we need to measure the impact. This is all the possibles because of this the big data analytics is happening there. That understand that where the losses is happening, where the gain is happening, and within the farm level, among the farmer level, why one farmer is growing very good and other farmer is like, for example, between the farms, and just look at the one farmer to the next farmer. There's one is going the 5 tons of the wheat yield, and next is just going about 3 tons. What's happening? That is that choosing the right varieties, or is managing the stress better way, is planting the crops in the right time so that is avoid the what's called desiccations or germination impact, looking at all those factors. So this is what required with holistic management to look at. I just give you that that's every farmer I treat as a kind of a unique. And the fingerprinting the farming systems are dynamics, so essentials. Just look at that. Anyone can guess what is this? This is just like a same rice farms. And we took it the hyperspectral data in the drones and the remote sensing, and looking at that one, like the same rice, the fallows after the rice is harvested. Some fallows are wet, some fallows are dry, some harvested much early, some harvested late, and some are fields are burned. What you can see, the scarce burns. Some are abandoned for almost like 1 or 2 years. Some they are immediately putting the different crops. So this is like I see that every farmer basically the way they choose the variety, when they plant, well, do they manage the soils and all the aspect of agronomy. That's basically making each kind of a uniqueness into the farm. How best to tap into that uniqueness to make a decision at the farm level. So I just look into the time series satellite the data, looking into those few selected spots of the rice. They all look different, but all are within the 50-kilometer radius, and this provides us so much variabilities in terms of the cropping system, rotations, management, all that aspect. So this really brings us what you call a long-term dynamics in the sustainable systems, integrations to look into large domain scales and identify those gap between one cropping season to other cropping seasons, how the Kharif is doing and how the Rabi is doing, and length of the cropping seasons, and all these informations that really helps to what you call a systematic management and understand the real-time the dynamics in the cropping systems, crop type, soil moisture, and variety suitability to the particular reasons are specific. So these tools are available. There is no there is no issue of developing the tools and technology. What is required is the collective actions, decision making, and the agro tagging. That's what makes integrates the what you call the local intelligence to the systems. So we can track what's happening in the systems and where the stress is happening and where the hard spot of the stress in the long term and the short term stress with the monsoons delayed and the monsoons bit early, and it's going to impact on the where are those going to be impact on the large domain. So this kind of analysis you can do it very quick way. I just giving considering the time. I just give one more example of real-time analytics of the farming systems, looking to all that factors. For example, here I want trying to understand in order to intensify that the area, the rice fallow systems and rice-based systems, monocropping into the crop diversifications with the legumes and vegetables, I need to understand the real-time analytics. We just look in the regular static the rice fallows. Look at that, a lot of the rice fallows available. We have so much of the rice fallows, I can make use of it. But you look at the reality in the real-time analytics, like when the rice is, some rice is harvested in the month of October. Basically, we did for every weekly basis, but aggregated it to the monthly just to simplify it. And then there is the quantum of the area harvested in October, and then in November, and then harvest is in December, and like that. And in January, some of the area is harvested. So that's basically what telling that. It's basically telling about the rice variety they are growing. It's early rice variety, what you call short duration rice varieties, and mid duration rice varieties, and long duration rice varieties. So basically, we're able to map that what the different area going, the different rice varieties are growing, and then simultaneously look into that what you call corresponding soil moisture. If the rice is harvested early, there's still the plenty of the October, still that's just the rainfall is ending. So there's still a lot of the soil moisture retained in the system. And so that you can usually that make use for the growing pulses. And if harvested in the month of November, and only a few area left over, but you harvested in the month of December, the most of the areas is become dry. So that's not making use of that. When you making use of the real time soil moisture stress, temperature conditions, and edaphic factors, and bring them to a real-time analytics, then you can identify the suitable areas for the specific crops or varieties and where you can target. So this kind of analytics can provide a better crop management and the stress management in terms of the providing the seeds in early right time of the year, and market analytics, and provide a value chains linked to the market and where you're going in terms of the providing the dal mills, so that instead of putting it to somewhere else, provide where the crops can grow so that they can process in the cheaper way. Are also linked to the market analytics where the farmers can sell that what you call the mobile based the farm phone, so that people can able to look into that, understand the e-mandis and look at, oh, this lentil is very the high rate in Calcutta rather than in the Dibrugarh, so that I can sell into there. So this is what required. That's linked again back to the managing the crops in a better way stress. And the important things about the disaggregation is scaling. What you do it at a small farm level or a district level, you can able to scale that into the big regions, state, and you can understand that dynamics in the real-time basis. Because of we are in the era of the real time. We want to see what's happening there. If the crop is cut today, I need to be able to know that. So this is what makes our augmentation technology much better. Then you can link that into the number of the mobile applications available and how the farmers, decision maker, extension system making use of that kind of analysis, and so that they can manage the crop stress conditions in the most integrated way, in the much better way. So here I'm giving again example of the rice fallow systems there, and look at the different. These are all the rice fallows used to left fallow after the rice is harvested, but we're able to map them in the right way and introduce the package of practices, and we can go into the right time. And this is the example what we did in West Bengal and Odisha. So we have to move away from the what we call a single commodity growing monocrop and leave the land fallow. We can grow the vegetables and the pulses in the residual soil moisture, including the understanding the water harvesting and water management. All the things will link into this one, what we call bring back to the dry areas into the green the scape. And also this links to the family farming, because of still 80% of the world population fed by the smallholder farmers. Still the family farming play important role in terms of the quality of the food and the nutrition. And the big pharma agriculture, they're not producing the high quality, the food. Instead, they're producing more industrial productions. This is the example I'm coming from my own farm as well, so that when the cotton is planted, I'm understanding here is how the stress management of cotton really works out. The simple here is growing a monthly harvestable crops like radish and leafy amaranth and coriander, dill, like that. You can grow in interface space between the cotton. Cotton still is growing, and they require at least 6 months to cover the canopy. You can make use of that space, and you can grow so that farmer can harvest like a monthly income, like a salaried person can get it. And the advantage here is because the interactions happening with a number of different species happening in the soil and mycelial and root zone level, and cotton become a kind of the herbs growing there, they become a kind of insect repellent and become resistance. And you instead of reducing too much of what you call spraying, it reduces the workload and reduces the crop, and cotton become a resistance to the basically instead of resistant, I would say. And that's the way you can reduce a lot of the management issues, input use, and that's basically brings the input efficiency. So that considering the time, I would like to conclude a few things here. Still, agriculture is the single largest lever to achieve the SDGs. When you look very close, deep into the 17 SDGs, and food plays an important role everywhere, whether it's malnutrition, employment, land degradations and desertifications and loss of biodiversity. This comes to the family farming and crop diversity. So there is certainly the need of the holistic management at system level required to better understand the climate, weather, and what's happening around within the soil, outside the soil, outside the environment, and link that into the farming system dynamics. So that reduces what you call the holistic the stress and the stressors. And there is the technology not issue. Let's leverage the technology like this augmentation. That's basically a combination of the earth observation, open access, machine learning, cloud computing, smartphones, citizen science. I think I put more emphasis on citizen science because one of the projects we've done, that one amount of the data coming from the farmers having the smartphones, amazing. So that you can put into your machine learning algorithms that provide the smarter, interoperable real-time analytics. That's really help us to understand the decisions and interventions and managing the crop stress of our whole system itself. So digital technologies are matured enough now. There's so much of that happening, but it's already matured enough to make good decisions. And that helps us to build an inclusive agroecosystem, but it needs a coordinated and collective effort among the disciplines and actors, because of this is the holistic management. Basically, you need to look into all the departments and the disciplines together, join the hands. That's where I call it as a holistic management. With that, just with a concluding remarks, production follows functions. Let's leverage the technology, local intelligence to rebuild the functional food systems for a sustainable future. So thank you so much for providing opportunity to speak about this one. Thank you so much, and I'm happy to take questions if any.
Thank you very much, Dr. Biradar. In fact, I should say that your rare combination of your type, wherein you had done a master's degree in genetic engineering and a PhD in geoinformatics, and so you have given a holistic overview of scale as a dimension, which rarely we could come across any of the presentations which try to give an holistic approach, and it has really justified the title of the presentation, sir. And we are very privileged to have you on this webinar, sir. I will quickly take one question. One question from Dr. K.V. Rao. What is the resolution of soil moisture data? Is the soil moisture data you mentioned available in public domain?
This what we did is we did the machine learning algorithms using the Sentinel data, including both Sentinel-1 and Sentinel-2, and we not estimated the volumetric. Instead of what we estimated, it is either the particular soil when the crop is harvested, it is wet, dry, or the soggy, what you call these only three categories you map that one, but this is available. Easy to algorithms, we can do it. And now we are building what is called a real-time rice valley information system intensifications, and we're putting that all these algorithms with open. And it's simple algorithms. So this is the data you can, because of all the systems are developing here is on the fly. You can calculate the district and calculate the area. It can calculate the soil moisture at the given date.
Oh, yes, sir. One last question, sir, from Priya Batra Santra from Kaji Jodhpur. Sir, can you throw some light on the accuracy and uncertainty of the geospatial map and the dependency of it with available data density and methodology used to prepare those maps?
Yeah, so I think this is the big the aspect itself, the geospatial resolutions, and that's determines the accuracy as well. And we need to look into the data is available from the sub-meters and few centimeters to the few kilometers, right? So the accuracy is depend on the scale we are looking at and analytics we are looking at it. So we need to understand what scale we are looking at. And of course, in general, I would say that most of what you look at, the accuracy of the data is in the crop types and land use land cover classification, for example, irrigated areas and are mapping these. So this pretty quite good achievable accuracy we are achieving this now at least more than 80%, I think. So that is what we see across the different scales. We did a very interesting study comparing different resolutions, like a drone level, like Sentinel level 10 meters and Landsat and MODIS. Of course, there's a compromise with resolutions and accuracy as we go in the larger scale. Other questions? Sorry, I forget.
Whether the moisture data, where would it be? Is it available in the public domain?
Yeah, I addressed that one because this is the on-the-fly calculations, and whatever is there in the online, so that you can select the date and things. What you're building is called the real-time analytics, so that you can choose the date, you can able to calculate the soil moisture for the given date.
Yes. So we'll share you the questions from the attendees on your email, so that probably if they
certainly I might have missed a lot of the questions and happy to address them.
Thank you very much, sir. Thank you very much, sir, for a very, very informative and very eye-catching slides as well. It's always a bliss to listen to you. And we foresee to have further collaborations in these areas from an National Institute of Abiotic Stress Management. Thank you very much, sir.
Thank you so much, Dr. Bhaskar and the team and director. I think we brought a very interesting team together to address a whole lot of the issues and the crop stress management. Thank you so much, and congratulations.
Yes, thank you. Now we have all the speakers. We have a very informative sessions with all those presentations. I would request Director of National Institute of Abiotic Stress Management, Dr. Himanshu Patel, sir, to give his concluding remarks to overview all those what has been presented, so that we can come up with the end of the session after the vote of the thanks from Dr. Sachin Pawar. Over to you, sir.
Thank you, Bhaskar. I think all of us should agree that it was a wonderful session. All the 6 presentations were so informative, so engrossing that we could really learn lots of things. Let me start with what Dr. Biradar said once, that we need stress-free agriculture. Very rightly said. Actually, we need to have stress-free agriculture. We need stress-free soil. We need stress-free water. We need stress-free environment. We need, of course, human beings stress-free. So we do not want stress. But unfortunately, there is stress everywhere. You know, there is abiotic stress, there is biotic stress and all. If you know that the oldest mantra, Shanti mantra, all of you might have read or heard sometimes, that we wanted Shanti, peace. Prithvi Shantihi, Apaha Shantihi, Aushadha Shantihi, Vanaspataya Shantihi, Vishwadeva Shanti. So all wanted to be totally stress-free with peace and everything. But we are not fortunate enough. There will be stress. There will be biotic as well as abiotic. That means we have to really address those stress. And to address those, we need geospatial temporal assessment at different levels. Policymakers may need it at a macro level. Maybe for them, even district, state, nation could be okay. But for a farmer, we need a very micro level, very, very micro level, because our farmers are very, very having small. So what we wanted today, and I think we have achieved that, we wanted to have a stock of all the knowledge on these particular aspects, whatever we have got. We also wanted to know how the things are being worked out, what they are trying to do, how they are doing this, and of course, what are the challenges and opportunities. And all these 6 presentations really gave us a detailed analysis of all of this, whether it is Dr. Amarnath from IMI, who talked about scalability, technology targeting, insurance, bundling, and all kinds of things. Dr. Srivastava talked about remote sensing, basic soil maps, geoportal data and informations. He very rightly talked about GPS and GIS-based soil fertility mapping, spectra-based soil analysis. Dr. Sirsat talked about crop loss assessment, insurance, all the methodological challenges. Dr. Suresh really taught us about artificial intelligence, machine learning, deep learning, artificial neural network, and he gave very good examples of each and every aspect. And then, of course, the concluding one by Dr. Biradar was really very, very informative, comprising all of these informations about digital augmentation, geo, big data analytics, and so on. Friends, as I said in the beginning, that we are having a very specific plan with us. We are already having a project in our institute, and we want to collaborate with not only the speakers of the day, but also others who have joined us today in this adventure. And then let us all work together to come out with a full-fledged system where we will be able to really provide good information to policymakers and also to farmers. Of course, there are challenges. As one of the participants, I think Priyabrata Satra talked about, that there are challenges of accuracy, there are challenges of uncertainty, there are challenges of scales, there are challenges of precision, and all of these things. But the major challenge is, of course, good quality data. But what I could see today, that though that is still a big limitation, but there are several agencies, there are several bodies, organizations with whom a fairly good amount of fairly quality data is also available. So now probably we need to compile all of those, bring everything together, and then of course, let us go ahead. As Dr. Biradar rightly said, that now we are in a new era of automation, and very rightly so. And not only planners, not only big policy makers, even our farmers, even some small farmers are very rapidly shifting to all kinds of tools. These are no more alien kind of things to them, and we have to really reach to them. Our today's event was just only the beginning of what we are planning. Many things are there, and what information, what knowledge, and what wisdom which we got today certainly will be very, very useful to us and also to all others who have attended to the event, so that we will be able to work together. I, on behalf of everybody from my institute, thank profusely to all the speakers for sharing their knowledge, for sharing their information, and I request all of them to be with us in the journey of our project also, and also we are committed to collaborate with them. I thank all the participants for questions, and of course my thanks certainly should go to the convener and also the co-convener who have worked really very, very hard. But as I said, this is the beginning. We will be working on it, and we really now need to start the journey for which we have planned. So thank you all. Thank you very much. Thank you.
Thank you.
Yes, sir. And the last in the process is a formal vote of thanks. I request Dr. Sachin Pawar to give the formal vote of thanks.
I think he needs to unmute.
Oh, I'm extremely sorry. Good afternoon, everyone. It is indeed my privilege to propose a vote of thanks on the occasion of this national webinar. First and foremost, I, on the behalf of ICAR NISM family, extend a very heartfelt thanks to all the honorable speakers who took out valuable time from their busy schedule and also poured a lot of efforts to come out with this enlightening presentation. Thank you, sirs. Next, on the behalf of webinar team, I wish to express my gratitude to Dr. Himanshu Pathak sir, Director ICAR NISM Baramati, for constantly supporting and encouraging us to conduct this webinar. Also, I would like to extend a special thanks to our convener, Dr. Bhaskar Gaikwad, for all the efforts in putting together this entire program and successfully organizing this webinar. I extend my thanks to special invitees, scientists, researchers, faculty members, project staff, and students for devoting their time, raising pertinent questions during the session, and making this webinar a success. At the end, the ICAR NISM family extends heartfelt gratitude to everyone for giving us this opportunity to be a platform for scientific discussion and thought sharing in the form of this webinar. We hope to receive overwhelming participation for our upcoming webinar series. Thank you, everyone. Have a good day and stay safe.
Thank you. Thank you, Dr. Pawar. We will be concluding this. Praveen, I request you to end this meeting. Can you?
Sorry, I got to leave to the other meeting, so
I'm extremely sorry, sir, that we could not tie up with your time. And
so my GCT meeting is happening. I just took off 30 minutes from that. I need to join. Thank you so much. All the best.
Thank you, sir. Thank you very much for sparing your valuable time and letting us know.
Bhaskar, yeah.
Yes.
Bhaskar, 1 minute before Praveen closes, all that chats that can be exported, ask him to export it into a file.
Yes, sir.
Okay,
yes,
that
sir,
will be good. Okay.
Yes, sir.
Congratulations, it's really very nice.
Thank
Okay.
you. Sir.
But ask Praveen to export, or you can export it as a co-host.
Yes, sir. We did it intermittently as well. And
yeah, it's the final one, all you will get at a time.
Yes, sir, definitely.
Okay.
We would do
great.
That.
Thank you.
Thank you. Praveen, can you have you exported the chat so that after doing it you can end with this session?
Okay,
yeah,
sure.
Please. Thank you, Praveen.